We're live. Almost. All right, perfect. So if you want perfect back coupling, you can now log on to the YouTube link as well. I don't recommend it. All right.
Minchia, dalle 3 alle 7 dura.
Sorry? Oh, and to the speakers, I will give you 2, 1, and 0 warnings. So when it's after 10 minutes, I will put this 2 up, and then after 11 minutes, I will put this 1 up. And then when your time is over and you're running into your question time, I will have the 0 here. All right. Awesome. My clock just jumped to 8 a.m. I have to times to go through the participants list. I would say let's get started. At the beginning, it's only me speaking, a few organizational things. So welcome everyone. I'm very happy that we can present the first SAZERAC-Sip, which will be about the first stars today for 4 hours. We'll be listening to amazing science. First of all, a big shout out to the two Steves for providing the SAZERAC conference format. It's really great. It made the life for us organizers much easier to have a web page, to have a Slack channel, and all this communication was really, really smooth. So thanks a lot for that. And also thank you to Will for checking that YouTube is working and that we will have nice recordings of all the talks. With my SOC, with Greg Bryan, Sultan Hyman, and John Weiss, it worked together really nicely. But it was very, very hard to decide for the talks that we actually are going to listen to today. So I'm very sorry for the ones that we don't have time for. It's just a one-day conference of only 4 hours because of the different time shifts. We would have loved to hear from all of you. Unfortunately, this was not possible because of the time, and I hope we can listen to your talks at one of the other SIPs. There are already 3 more other SAZERAC-Sips announced. So just very short to the organizational things. We do have a Slack channel, a Slack workspace associated with this conference. You can find it with the hashtag #SIP-1stars. The invitation to the Slack channel is the same as for the summer SAZERAC. You should have found it in that email that you clicked on this link to actually go to the Zoom session. And for talks, we're going to handle it as we did it with the summer SAZERAC. So in this Slack channel, so in this SIP-1stars, I put already all the titles for the talks in. And then during the talk and after the talk, you have time to ask your questions and put them directly in this thread for the talk. So don't put it at the bottom of the Slack channel because I can't have my eyes everywhere and then it gets confusing. So please reply to the thread and ask your question there. Don't unmute, we want to stay muted for the entire time with too many participants to have a direct discussions. But what we will do, I'm the session chair for the first session. Zoltan is the session chair for the session after the break. And we will go to the Slack channel and we will look at the questions that have been asked. And then we will choose the most relevant ones. So if you like a question from somebody else, give them a thumbs up so we can see that this has an interest in several people. So please stay muted and for most of the time with the video off so that we don't get a bandpass problem. And then Zoltan and I will, in our respective sessions, will look at the question that all of you have asked. And then we will ask those live to the speaker. Typically, in summer, we had too many questions. The talks were great and very interesting. And I expect the same to happen here. So what we think we'll do is we ask the speakers to then later go to the Slack channel after they finish their talk and cooled off a little bit to answer those questions there. And there you can have a nice discussion in embarking, similar to what would have been a coffee break in normal times. So yeah, you can see here at the bottom of my page, you can see the scheduled. We have 4 hours in total. We will take a break after 1 hour, 45 minutes of half an hour in which the speakers for the second round can set up and everyone can take a deep breath, leave the computer screen for a few minutes. And our first talk is going to be an invited talk by Tilman. And I'm very excited for that. Because he told me it's going to be interactive and we worked on that together. So that's, yeah, I hope we start off with a great talk. And yeah, unless there are any really pressing immediate questions or comments from my co-hosts, I would say, take it away, Tilman, and have fun at this conference.
Okay, thank you very much, Anna, and good evening from Tokyo to everyone. It's a great pleasure, it's a great honor to open this exciting conference. So thanks a lot for the organizers, for, well, the organization, and for having me giving this overview of the first stars. And I have to admit it's challenging to summarize this broad topic in about 20 minutes, but I will try my best. So first, a small, motivation and introduction why we actually care about the first stars. And so for those who are already in the field, that's more a reminder. For those who are new to the field or students, that's the motivation. And I would say we should care about the first stars because, well, they set the scene for everything that happens afterwards. So they shape the first galaxies. Their radiative, chemical, and mechanical feedback basically sets the scene for galaxy formation. And the first stars may provide the seeds for the first supermassive black holes, and they provide the first heavy elements. Now, their contribution to all these feedback channels depends on their stellar masses. And the initial mass function of the first stars, which exactly quantifies the distribution of stellar masses of the first stars, is largely unknown. This is because, well, the first stars, they are too far away in space and time, so we cannot observe them directly, and we only have indirect constraints from observations and simulations. And so that's just a qualitative illustration. So we should care about the first stars and better understand them so that we can better judge what is exactly their contribution to these feedback mechanisms. Now, we will come back to the IMF, but let's first ask the question, under what conditions do the first stars form in the early universe? In what environment? And usually the condition, as always for star formation, is you need to have cold gas. In the early universe, the only main coolant is molecular hydrogen. So the condition is you need to build up a halo that is massive enough to contract gas so that you can then, well, form molecular hydrogen and cool down. That is usually quantified by the critical mass. And here we see a function, or this as a function of redshift. And I would like to draw your attention to two recent studies by Anna Schauer in blue and Mihir Kulkarni in green. These were the first simulations that both included Lyman-Werner and baryonic streaming. These are both effects that we think they will delay and suppress POP3 star formation, or, well, delay or even suppress. And so if a halo is above this threshold, it is expected to form POP3 stars. And the interesting thing that I find here is this discrepancy, especially at high redshift, of about 1 order of magnitude. And I will not go into this now because Mihir Kulkarni will later give a talk on, I think, this topic. So we can look forward to this. But I think roughly we can say, well, the first stars form at redshift maybe above 10 to 30 in mini halos around 10 to the 6 mass. 10 to the 6 solar masses. Now, coming back to the POP3 IMF, and now comes the interactive part where I need your help. So I called this the democratic initial mass function, and I will launch a poll in Zoom. And the question is simple. The standard POP3 IMF contains stars of which masses? So it's a multiple choice poll. You can select your the mass range that you think the first stars would, well, inhabit. You should see the poll now. I will give you some time just to explain what I mean with the standard POP3 initial mass function. So we know that POP3 stars, if there is a strong Lyman-Werner background, then we may form supermassive stars instead. And so that's not what I mean. So the standard is in isolated halos without external feedback. And just realize probably the hosts and co-hosts cannot poll right now. But I'm seeing already 20, 25 people. I will wait a bit so that this can grow. It's a beautiful histogram already. All right, I can also on my, wait 1 second. Let me just do this. Okay, 50. And right, not everybody has to submit their answer. So if someone thinks, well, I don't know enough, then we can wait. Okay, we should not do this for too long. Already 70% of people have replied. I will give you 5 more seconds because it goes from my precious time. Okay, I will and the poll, and I will share the results, and I will also try to make a screenshot that I don't forget it. And I think now you should see the results. So this is our democratic POP3 initial mass function. I will not comment on it now. I will make maybe a nice figure out of it and put it on Slack. And it would be interesting maybe afterwards to do this poll again if we have time. Let's see. But for the moment, let's go back to my presentation. So that was the, it's loading. Yes, that was the democratic POP3 initial mass function. All right, maybe, sorry, you have to close the poll if it's still open on your screen. And so that was the democratic. And now let's see what the simulations have to say on this same topic. So I like this form of overview. What I show here is the expected mass range from various simulations as a function of the year of publication. You may have seen a similar plot from me before, but I have updated it with some new results. So this is more qualitative, the mass range. And what we see is kind of a decrease over time, which I would assign to a better numerical resolution in the simulations, so that around 2010, people can actually resolve the fragmentation of smaller clumps. And well, I think later we will hear also talk by Sugimura-san, and he may tell us what's special in his simulation. But roughly, we still see a scatter, and I would not say that this has converged yet. So this is still open for improvements. And it's maybe also unfair, some of these comparisons, because these are just different simulation codes and different physics included. So to have an overview of exactly the physics included, this is a really nice compilation done by Piyush Shadar, and I just added a few information where he compared different 3D simulations of POP3 star formation and the different physics that is included. So AMR, adaptive measure refinement, that's the simulation technique, if the chemistry is followed, if turbulence is resolved, if magnetic fields and radiative feedbacks are included, and then if fragments evolve in this simulation. So what you can see, well, first is a large diversity. And interestingly, at least these criteria defined by Piyush, non-simulation or no simulation so far has included all these. So there's still room for improvement. However, it's always easy to say from the simulation side, hey, we need to improve the physics. And yes, we need, but what else do we need to do? And especially, I think one problem is the time that we need to push the simulations. And on this, Hachime Souza last year made a very nice, almost a meta study. So he came up with some scaling relations between the time and the threshold density that allows us to compare different simulations of POP3 star formation. And what we see here is the number of fragments as a function of time after the first protostar. And so what he shows is also analytically that there is some power law relation to the power of 0.3. And most simulations with very different codes and approaches follow this relation. But now the question is, for how long do we have to simulate? And the argument is that roughly after 1,000 to 10,000 years, we would expect protostellar feedback to terminate star formation. So to prevent the formation of new clumps and to stop accretion onto existing clumps. So I would say, and Hachime Souza would say, we would need to simulate roughly 1 order of magnitude longer so that we actually see a convergence of the mass distribution. Now, these were the constraints from numerical simulations. In the next few slides, I want to highlight what we know from observations, the indirect constraints, and I think the most important one is stellar archaeology or extremely metal-poor stars. The idea here is these extremely metal-poor stars, they have formed in the early universe, and then they have conserved their chemical composition until the present day. So if in the present day universe we see these old metal-poor stars, we basically see the fingerprint of POP3 supernovae. And so what we can then do is we take the chemical composition of these old metal-poor stars And we compare it to what we think are the supernova yields of the first stars. And this, what we see here, is a study by Miho Ishigaki. And what she did is she took a sample of around 200 extremely metal-poor stars and did exactly this matching of progenitor supernovae. And what she finds is this distribution. The different colors are different explosion energies. And it roughly clusters around progenitor masses of 25. And while I think this is very informative and one of the most complete studies of this kind, it's of course very limited and biased, because with this method, we can only probe the mass range where we expect the chemical signature, which here is the core collapse supernova range. And for example, but that's a different issue, so far we have not detected the chemical signature of pair instability supernovae. So another thing that metal-poor stars can tell us is about the POP3 multiplicity. And there will be also a talk by Louise later, and she also had a paper on exactly this just yesterday, so you should all check it out. However, the figure here is from myself and Miho Ishigaki. What we did here is with supervised machine learning, we took 500 metal-poor stars and classified them depending on the number of enriching supernovae. And so these are the bins that you can see here from 1 to 5. And we would claim that the number of enriching supernovae corresponds to the number of POP3 stars, or POP3 supernovae per mini halo. And so what we find that most of them are mono-enriched, so just enriched by one previous supernova, but we see a tail of multi-enriched, extremely metal-poor stars. And so this allows us to investigate the POP3 multiplicity. And to you, this may look like a simple histogram, but this is like 2 years of hard work, and we hope that we can finish the paper soon. So there will be further talks also later on the POP3 binary statistics, which are of course related to multiplicity. And the last point, what extremely metal-poor stars can reveal about the first stars, is on the low mass end. And here the idea is, if the first stars are, if their mass is less than 0.8 solar masses, then they should survive until the present day. And we should see them as metal-poor stars. And so this is a study by Mathis Mack, which shows the probability of not detecting metal-free stars in the Milky Way as a function of the Milky Way halo mass. So this dimension is just because we're not exactly sure. So they've done several realization of Milky Way-like merger trees. And other people have done this before, but the new insight from Mathis is the following. Instead of asking what fraction of all stars in the Milky Way could be POP3 survivors, his insight was, well, finding POP3 survivors, it's the same strategy as finding extremely metal-poor stars. And so it makes more sense to compare what fraction of extremely metal-poor stars should be metal-free stars. And with this, he can get very tight constraints on the survival. And basically, the bulk of these points is below 1%. And ultra metal-poor stars are more constraining than extremely metal-poor stars. But basically, from here, we can conclude with 99% credibility that there are no metal-free stars that have survived until the present day. So this was stellar archaeology and metal-poor stars. Now I have one slide on further constraints. I said 20 minutes is tough to summarize everything. So let me just mention what else is possible. For example, gravitational waves could show us, and maybe are already showing us, some idea of the remnants of the first stars. Then a super exciting paper by Anna Schauer on the ultimately large telescope, an infrared telescope with a 100 diameter dish on the moon that could eventually ultimately find the first stars. Or the 21 centimeter signal, where we need some additional heating cooling to explain this, which may come from the first stars. Or the direct detection of supernovae at high redshift. And a long list of other constraints. However, I would argue, and I'm happy to discuss later, so far these are mostly non-detections or upper limits. And so therefore, I would say it's not further constraints at the moment, it's more like future constraints. Because we need either, well, new facilities to detect those, or like for the gravitational wave, we need maybe 1 or 2 more decades to have some statistics to see different populations in the black holes. But still, it's interesting to see the effect that POP3 stars could have on these observables. Now, on the last two slides, let me allow a bit of self-advertisement, but it's of course also in the spirit for the community. I want to mention SLOTH, which stands for Ancient Stars and Local Observables by Tracing Halos, which I think is also not the worst acronym in astronomy. And SLOTH is a semi-analytical model of star and structure formation. And the model mostly focuses on the first stars, second generation stars, extremely metal poor stars, but can simulate down to redshift 0. So if you want to know more technical details, either contact me or look at these papers from my collaborators on this project. And just one slide on what a SLOTH can do for you. So a SLOTH usually operates on megaparsec scales. So for example, we can simulate Milky Way-like galaxies. And if you now have a simulation on much smaller scales, so if you simulate POP3 star formation, really the fragmentation, or if you have a new seeding scenario for supermassive black holes, or if you have a new table of yields of the first supernovae, you could implement those into a SLOTH and then see what is the effect on large scales, what are the statistics, or how likely are those conditions to be realized under cosmological conditions. On the other side, if you have large cosmological simulations, which do not allow sufficient resolution to resolve, for example, the formation of the first stars, then you could also use a SLOTH as a subgrid model and either tabulate or run it in parallel. And so a SLOTH could help you with your subgrid physics in bigger simulations. A SLOTH is semi-analytic, so it's quite fast. It's parallel, and so therefore it's also good for parameter exploration. And we hope that we can make it public in a few months. We're working on it. So that brings me to my last slide, to the conclusion, to the open questions. One could condense it to 2 open questions. That is, what is the critical halo mass for POP3 star formation? And maybe Mihir will talk about this later. And what is the POP3 IMF? However, the second question, we can maybe add a few more details. So from the POP3 simulations, I think we need to run for longer. And if we believe Hajime Souza, we need to run roughly 10 times longer than what we're doing right now. And we need to add more physics, or simulations need to be self-consistent, for example, with magnetic fields and feedback. And then I would say, and I'm happy to discuss, that stellar archaeology at the moment is the most informative observational constraint that we have. And for example, stellar archaeology allows us to say that there are no metal-free survivors. If this means no POP3 survivors, it's a different question. So still room for additional research. Then the multiplicity and the binarity of POP3 stars. So I and Louise have provided some first hints into this field from the observational side, but still not the final word. And one thing that I have not spoken about in detail are parent stability supernovae, which are theoretically a very robust prediction. But where are they? We haven't seen their chemical signature, and not, at least not convincingly, or their light curves. And so there is still a lot of work to do. I hope a lot of exciting work to do. And I'm looking forward to the remaining talks, because they will cover some of these and maybe show the recent progress on these open questions. So that's from my side, and thank you very much. And we have more time for questions.
Thanks a lot, Tilman. This was a great introduction into the topic. Please, everyone, stay muted and post your questions on Slack, and I will read them out. We have a very first question already by Stefan. It says, regarding the plot of critical halo mass versus redshift, what happens if you to higher redshift? Can you convolve the redshift evolving halo mass function to get star formation rate versus redshift?
So the question, sorry, because I was dealing with things, was what happens at higher redshift, and can we convert this into a star formation rate density? Yeah.
Yes.
Right. To answer like what happens with these functions at higher redshift, I would rather refer to Anna or Mihir, who could answer this better. The idea is basically, I mean, you need a minimum halo mass. And also these are, one has to say, these are extrapolations. So I just know, for example, Anna had only halos in a certain redshift range, I think around 14 to 24, well, whatever. But here 30-40 definitely is extrapolated to higher redshift. And also the baryonic streaming at this high redshift would be even stronger. So maybe they even would go up. So right, I cannot say exactly what would happen with these functions. But now for the star formation rate, yes. It's probably not an easy conversion because there is feedback. And I think that's also what Eli and Mihir will talk about later. But in principle, this convolved with some halo mass function allows us to derive some star formation rate density at high redshift. Something that a sloth can also do, for example.
Awesome. Then Naoki is asking, SUSA plot is showing increasing number of small fragments and the constraints on the fraction of low mass population 3 stars can't be easily made consistent. So I think the question is, apparently there's a tension, and what your thoughts are on that you cannot really combine this work from SUSA with a low mass population 3 star constraints.
Okay, good point. So the point is that if the extrapolation is true, then maybe we expect dozens of POP3 fragments, and then it would be likely that some of them are low mass, and that is in tension with the no metal-free survivors. Okay, if I correctly summarize the question, and I agree, that would be a tension, and therefore I try to emphasize that their survival is for metal-free stars, not for POP3 survivors, no metal-free survivors. And so there is another discussion about possible pollution. So it could be that the first stars have low masses that form in the early universe, and then their surface is polluted with metals from the ISM. So we would not see them as metal-free survivors. Right, I don't know if this solves the tension, but maybe at least it mitigates the tension.
That's a start. Gen says, great talk. In your new results with Miho, you compared the sum of elemental abundance with the observed stars. If so, how is the statistical noise in the 5 population 3 stars case?
The statistical noise in the 5s on this high spin. So I don't know if that's exactly the statistical noise, but definitely there are very high degeneracies. And that's also, so this NA bin is exactly the ones where our classification is just not reliable enough. We have checked that there is no bias. So even if we change the threshold, the relative height of these does not change. But right, to discriminate an extremely metal poor star that was enriched by 4 supernovae or by 5 supernovae, it's really just statistical minor significance. So, right, there is scatter or at least uncertainty, which we try to quantify in this bin, but at least the qualitative message is not affected by this.
Okay, awesome. And we have a last question by Zoltan. How sensitive is the ULT on the moon? Say, what is the mass of a POP3 star cluster? What is the mass of a POP3 star cluster at redshift 10 that it can detect? Shall I just answer that?
Please, yes.
So we designed it with reference to Angel et al. 2008, so that we have a fiducial mass of 1,000 solar masses. It can reach down to a little bit lower than that. It depends on the IMF. So I would say the lowest mass end is roughly 500 solar masses, depending on the IMF. But it's designed for 1,000. Okay. I think we have, like Tilman, please check out the Slack. I think now more questions are coming in, but for the sake of keeping this in time, I would say thank you again so much, and let's move on to our next speaker, Shingo. Shingo, please take it away.
Okay, could you see my slide? Yeah, okay.
And we can hear you.
Okay, so I'm Shingo Hirano from Japan. And okay, so today I will talk about my recent work about the supermassive formation on the dynamical gas cloud. So this is a problem of the high mass end of the populace IMF, as shown in Tilman talk. So today I show my numeric simulation of the my magnetic hydrodynamic simulation result of the supermassive formation in magnetized atomic cooling gas cloud, and how the and show the effect of the magnetic field on the supermassive formation. Okay. So this slide, in this slide, I would like to show the motivation of this study. So the goal of this study is to show the formation channel of the seed black hole of the high-Z quasar or supermassive black hole, which observed at redshift 6 or more. And such a very, very massive object with about 10 to 9 solar masses is observed, but the origin is unclear. And to form such a very massive object, we should explain the formation of the very massive object about 10 to 5 solar mass as the first formation error, which is called as an intermediate mass black hole, or IMBH. And one possible channel of such a one possible formation channel of such a supermassive object is the direct black hole scenario, and which is about the rapid collapse of the chemically pristine, so zero metallicity gas cloud with 10 to 5 solar mass, and which forms about the same mass supermassive star and same mass black hole. Okay. So, previously, many researchers studies such a formation channel. And to form such a very massive black hole, researchers consider the atomic cooling halo, because inside such a halo, the very high accretion rate and the constraints of the fragmentation are realized. And until now, many formation channel is considered as listed here. So this pointer. Okay, so as listed here. So, and theorists should answer the sum of the formation rate of the SMB seed and compare such a formation rate with the observation rate of the high-Z quasar. So this is the current condition of this topic. But there is one unexplored factor of this study. It is the magnetic effect, and this is the main actor in this talk. So because the magnetic field in the universe are considered to weak, so emission effects are usually neglected in the previous study or the many simulations. However, in some study and also recent studies says during the star formation during the first star formation, some amplification process can enhance such a tiny B field to the very significant value, and such a strong magnetic field can affect the accretion history, fragmentation, and final stellar mass of the first star and first supermassive star. And in the supermassive first star formation cases, recently Gray et al. Shows the simulation of the magnetized atomic cooling halos, and and they show the amplification problem, amplification process of the such a primordial very tiny B field, but B field. However, they stop simulations at the end of the collapse phase. So at the era of the formation of the stellar core, and they didn't study the magnetic effect during the accretion phase. So in this study, I'd like to check the effect of the influence of magnetic effect during the early accretion phase by performing the MHD simulations. Okay, so in this slide, I summarize my simulation setting in this slide. I use MHD simulation, non-ideal MHD simulation code I used in my previous studies, and the important point is I changed two parameters of in this study. One is the initial magnetic field strength from the zero, non-magnetic cases, and from 10 to minus 12 Gauss. This is the typical value in the at the formation versus formation error. And 10 to minus 5 Gauss. This is very, very strong cases, and similar with the predicted star formation. And as a second parameter, I change is metallicity. The one case is the solistic case, so zero metallicity case, and one is a bit metal energy case, so bits 10 to minus 4 solar metallicity. It is because in recent study by John and Omkai, they show the formation channel of the supermassive first star in such a metal energy case. So I also checked the magnetic effect on such a case. Okay, and in the later in the following slide, I will mainly show the physical cases with initial B field with 10 to minus 12 Gauss and the general case. So I will call this as a physical model. Okay, so let's go to the physical result. So in this slide, I show the result of the physical model and the first evolution of the first 300 years after the first dense core formation. So, or in other words, the first star formation. And in the below three panels, I show the to the density map and B field strength and the proton beta value, which is the ratio of the thermal pressure and the magnetic pressure. So this shows the importance of the magnetic pressure, the magnetic effect compared with the thermal effect. So let's go. So let's start the movie. Okay. So just after. So and this is just after the first formation cases, and after the first formation, the second and third fragments forms, and nearby such a small tiny fragment, the B field, the magnetic field are strongly amplified, because such a small tiny field, because the moving and rotation of such a small tiny core can efficiently amplify such a B field. And as a result, the proton beta value decline strongly, and it means the B field effect becomes important. And as a formation of the multiple fragment, the B field, the strong B field region expand. So this is the basic result of my simulation. Okay, so let's let's summarize the result as this slide. So this figure shows the radial profile of the density and B field. So at the time 0, or just after the first protostar formation, the B field strength becomes 10 to 6 Gauss as a center of the protostar. However, just after the 10 years, the the B field quickly amplifies to 10 to -2 Gauss. This is due to the rotation around the first core, the first dense core. And after the 100 year and 500 year, such an amplified region expand due to the formation of the following the later dense core and its rotation. So this is so this means during the accretion phase or during the very early accretion phase, the B field strength can amplify around the surface regions. Okay, and this slide shows the evolution fragment the fragment properties. So number and mass of fragment. So because of the very efficient merger, the merger rate, the fragment number is not so different. Not so different. However, the most of the fragment can merge to the primary one. So the most of the fragment mass is held by the primary core or central one. So this small figure shows the mass spectral, and you can find the primary core have the most of the mass. Okay. Okay, and this slide shows the comparison of the magnetic case and non-magnetic cases, and I find by adding the magnetic effect, the mass growth of the total mass of fragment and the primary fragment differ greatly. Okay, so in the last slide, I will show you the dependence of the two parameters. One is the initial B field strength, and I find so this figure, so this line color shows a different initial B field strength, and the yellow color shows a very strong initial B field, and blue color shows the tiny B field. In the case with a very strong B field, about 10 to 5 or 10 to -6 Gauss cases, in these cases, the very early supermassive formation can occur due to the strong angular transfer and the merger rate, I find. But in other cases, the growth, the amplification, and the time growth is very similar. And finally, I show the effect in the case of the metal ended cases. And in such in metal gas clouds, because of the low temperature of this cloud, the mass accretion rate decrease. However, in the case with the very very high initial B field cases, which can occur in the metal cloud, which experience the faster formation. The very massive supermassive star formation can occur. So this is this shows this just supports the formation of the supermassive fast star in the metal cases. This is the final result of this talk. This is the summary slides, and I end my talk with this slide. Thank you.
Thank you so much, Shingo. Those are amazing simulations. Thanks so much. Simon is asking, how do you enforce the divergence of the B field is equal to 0 constraints in these simulations? What's your method?
Okay, I find your question in Slack.
Yes, diff B equals 0.
Ah, okay. Okay, I check it in and
like, how do you force that this is happening in your simulations?
I'm sorry. Sorry, Simon. I can answer it after my talk in Slack.
Yeah, it sounds like a very technical. That sounds great. John also has a question, and he wants to know if you tested to see if the small-scale dynamo is enhanced, if the genes length is better resolved, referring to Federat and Turk, who went up to 128 cells per genes length. So I think this is also a resolution question.
Yeah, it is important questions, and in this simulation, I didn't change the resolution during the collapse phase, and in collapse phase. So as your questions, if I enhance the resolution, the resolution, the initial amplification factor can be enhanced. However, I think such a difference can be tested by in my simulation by changing the initial B field strength, because this difference can give the same result with resolving the high resolution cases, I think.
Okay. That sounds good. Shingo, you have quite a few more questions on the Slack. I would refer you to those. So thanks a lot. It was a very nice talk. And let's continue with the formation of the first star binaries by Kazu Sugimura. Thank you.
Okay, do you see my screen?
Perfectly.
Okay, so thank you very much. And first of all, I would like to thank the organizer for giving me a chance to talk here. So today I would like to talk about our recent simulation of formation of the first star binary, and as shown in this background image. And this talk is mostly based on this paper in collaboration with Matsumoto-san, Hosokawa-san, Hirano-san, and Omkai-san. So I'm Kazuyuki from University of Maryland, and let me start my talk. So content of my talk is like this. So I first make an introduction for first star as well as first star binary, and then I will talk about our new code, SUSMAT-RT, and as well as our simulation setup, and then I will talk about our result of our simulation, and I will finally conclude my talk and introduction. So because Tilman already gave us very nice review, so I just briefly explain this slide. So the first star formation drastically changed the history of the state of the universe, and the first star or pop-3 star, so both of which I use interchangeably in this talk, affect the universe in the form of like stellar radiation, supernovae, Xray binary, by bringing radiation metals or energies into the universe. And because these processes sensitively depend on the property of the first star, so it is important to reveal the property of the first star to understand the history of the universe. And in this talk, I will put a particular focus on the first star binaries or multiples. So why are they so important? And I will give 4 reasons for this. And firstly, so first star binaries or multiples can be the dominant population of the first stars. So in local observation, so present-day massive stars are often in multiple systems, and the pop-3 stars, first stars, although different population, but they are often considered to be massive, so they may dominantly belong to multiple systems. And secondly, first star binaries can modify the later evolution of the universe, as I said. So the physics leading to binary formation should modify the property of the first star, such as mass and Xray binary abundance, and in turn affect the later evolution of the universe. And thirdly, first star binaries are the good candidate for the progenitor of the observed black hole mergers. And finally, and importantly, so the first star binaries of multiple formation are suggested by former simulation focusing on the early phase of the first star formation, like these papers. So in those simulations, so they show that the initial fragmentation leads to multiple protostar formation, although their final fate was still unclear because this simulation only focused on the early phase. So in order to understand the final fate of those protostars, we need to follow the entire star formation process until the accretion ends due to the radiation feedback. So these two papers are among those attempts, and in this SPH simulation in SUSA 2014, they follow the formation of multiple fast star formation. But in the simulation, they were not able to follow the propagation of ionizing radiation because of insufficient resolution in low density ionized bubble, although ionizing radiation feedback is known to play an important role in the fast star formation. In this spherical grid simulation in Hosokawa 2016, so they were able to follow the fast star formation considering the ionizing radiation. However, so their code can only consider the radiation from the central protostar, and also their resolution is not sufficient in the off-center region where fragmentation leads to multiple protostar formation. So after all, so no formal simulation could properly follow the POP3 binary formation, and we decided to perform new simulation with a new code. So that is our motivation of this work. And let's move on to the method. So this is the recipe for our new code, SUFMAT-RT. So I developed this code by adding new features to original code SUFMAT. And to this self-gravitational AMR code SUFMAT, I added adaptive ray tracing module to solve the radiation transfer from multiple protostars, and also POP3 physics module to solve the chemical and thermal evolution of gas, as well as protostellar evolution. And with these ingredients, this code, SUFMAT-RT, is now able to follow the POP3 binary formation with self-consistent physics. And we obtained the initial condition for our simulation in this way. So to study the fast star formation in the context of cosmological context, we first performed the cosmological hydro simulation using gadget, and we picked up 2 mini halos for our simulation when their central density reached 10 to 6 hydrogen atoms per cubic centimeter. And we remap this data to a SUFMAT grid and like this, and we start our simulation using this initial condition. So this slide summarizes our simulation setup. And as I said, we performed the simulation of fast star formation in 2 mini halos from a cosmological initial condition. And those halos actually are the same as the case D, C, and D in former work of Hosokawa 2016. And in their simulation, the fast star mass evolve like this, and case C and D correspond to those lines. And because of this, so we call this and this halo as typical and low mass POP3 star formation size in this talk. And box size of our simulation is 10 to 5 AU, and sync radius and minimum cell sizes are 64 AU and 4 AU respectively. And defined comment condition and computation costs are like this. So as I said, so I performed the simulation from the same initial condition as the former work. So what's new to this specific work? Firstly, so adaptive ray tracing method in our code makes it possible to treat radiation from multiple protostars. And secondly, so adaptive mesh refinement in the code makes it possible to achieve much higher, so about 10 times higher resolution around off-center protostars. So because of these differences, we expect to obtain different results. And as we will see, that's actually the case. So let's move on to the result. And firstly, I'd like to show the result for the case C, which is a typical POP3 star formation site. And this is the movie for the simulation. So let me start. So this is the initial condition, and the 3D rendering of gas density is shown here. And I start our simulation from the collapse phase. So the central part, the density increases in a runaway fashion in the beginning. And I'm zooming the camera to the center. And at the center, fast protostar form. And the disk around this fast protostar is relatively massive to this low mass central protostar. So it easily fragmented into multiple protostars like this. But they also merge each other, and finally, so binary system remains after this phase. And these binary stars accrete gas from a circumbinary disk through this their own circumstellar disk. And also, we see this yellow region, which corresponds to the ionized bubble, so bipolar ionized bubble formed due to the radiation from each protostar. And as time goes on, so one of the disks, so circumstellar disks, becomes so massive that it is fragmented into a mini-triplet system, as you probably can see in this movie. And yes, and this ionized bipolar ionized region, its size increases with time, and the gas around this the gas around this mini-triplet system is now completely photoionized, and the accretion to this system is completely stopped at this time. But the accretion to the other star still continues at this moment through its own circumstellar disk. But this disk is also photoevaporated due to the internal radiation from the central star and from the external radiation from the mini-triplet system. And at the end of our simulation, the accretion rate to this central star is already very low. And we can say that the property of this stellar system is already fixed at this moment. And this summarizes the evolution of protostars in our simulation, and I plot the mass and accretion rate and separation of protostars as a function of time since the first sync formation. And each line corresponds to the each protostar. So as we saw in the movie, so we observed the 5 evolutionary phases: the gravitational collapse, initial fragmentation, binary accretion, rate time fragmentation, and photoevaporation. And as you can see, so many protostars form, but they merge and binary remain. And one of the disks fragment into mini-triplet system, and they evolve to this time. And at the end of our simulation, so the accretion rate already very low, and we can say basically follow the entire star formation process in this case. And this is the resulting stellar system for a typical POP3 star formation site. And we found a wide binary of massive single and multiple mini-triplet system like this. And both of them contain the massive star with mass larger than 60 solar masses. And this is our main result. And we also performed another simulation for case D, which is the formation site of low mass POP3 stars. And this is the result for this case. So in this halo, we observed the formation of three protostars, but they merge each other, and only 2 stars remain and form the binary. And this is the resulting stellar system. And again, we see the wide binary of unequal massive stars. And in summary, so we observed the massive binary formation in 2 out of 2 examined cases. And these results may suggest that the POP3 stars, so substantial fraction of POP3 stars form in massive binary or multiple stellar system. So I think I already ran out of my time, so I will stop here. So thank you very much.
Thank you very much. Another set of super great simulations. It's amazing progress. We have a question already by Rafil. That is, how far can you go in time predicting effectively the final masses of these binaries by following their current rates of mass accretion?
Okay. So I did 2 simulations, but maybe this one is the fiduciary one, so I will explain this. So in this case, so I performed the simulation for 1.2 times 10 to 5 year, which is very long. And at the end of our simulation, the accretion rate, so each line corresponds to the accretion rate, each protostar or maybe already star in this simulation, and they are already very low at the end. And the accretion to this single system still large at this time, but it also gradually decreases, and it's already below 10 to minus 4. And if we extrapolate this line, so the mass increase in later time is very low. Maybe the stellar mass is about 70 solar mass, but the mass increase is maybe less than a few. So I think we can safely say that the final state of this system is already formed at this time.
Awesome. So you say you reached the SUSA sun diagram to the right.
So I think related to Sassano's diagram, so I did the very long simulation, but the resolution is not as good as other simulation. So there are some compensation. So I was not able to observe the formation of very small, very tiny protostars. So I also need to do some simulation with a higher resolution to study such objects.
Okay, thank you.
Point.
I can ask you one more question, and that is by Rafaela, asking about that she sees you not exploring a wide range of initial conditions, but do you find any dependence of the binary separation or multiplicity on environmental properties?
Mm-hmm. I think environmental property or maybe initial condition of mini-halo determines the property of the mass as well as binary separation. But we have only studied 2 cases yet, and we plan to increase the sample, and then we can know the statistical property. But it's very important, but it's our kind of future direction. So
awesome, that looks great. I would also like to refer you to Slack. You have a lot of questions going on. And with that, thanks again for your talk. And let's move on to our next speaker, also talking about binaries, coming home to UT Austin. So Shingo, please, Boyuan, please take it from here.
All right, thank you. Okay, can you see my title slide?
Yes, but not yet in presenter mode.
Great.
Now
okay, hello everyone. I'm Boyuan Liu from UT Austin, and first I'd like to thank the organizer of this virtual conference. It's my pleasure to share with you my recent research for the statistics of population 3 binaries and their implications on early structure formation. This talk is based on some of our recent papers. I think most results will be from this paper, Dynamical Evolution of POP3 stellar systems and the resulting binary statistics. Okay, here is the outline of my talk. Let's get started. So why do we care about binaries? This is also mentioned by previous speakers. Binaries are actually important for understanding the observational signatures and imprints of the first stars. First, with close binary interactions, the stellar evolution can be changed, and this will change how stars look like directly. Second, contamination from the wings of companion stars and different supernova conditions shaped by close binary interactions can change the abundance patterns of extremely metal Perth stars that we can observe today. So this will also affect stellar archaeology. Last but not least, binary stars are also progenitors of Xray binaries and black hole binaries. Xray binaries can have very interesting feedback on the formation of the first galaxies and also the thermal evolution of the AGM. For example, can be recorded in the 21 centimeter signal. I think our next speaker will talk more. And also for binary black holes, if they could merge within the Hubble time, they will be important sources of gravitational waves. Actually, some of the events detected by LIGO could be from POP3 stars. So binaries are important. However, it is challenging to study POP3 binaries because we don't have direct observation, and we have to rely on theoretical models. Here, this plot shows the standard picture of POP3 star formation. At the beginning, we have a collapsing cloud. Then a protostellar disk is formed. In this disk, fragmentation and accretion onto protostars will continue until feedback shut them down. I call this phase phase 1. Thereafter, we have a newly born cluster of POP3 stars, and then binaries of stars will also further be formed by n-body dynamics in this cluster. I call this phase 2. As also mentioned by our previous speakers, due to limited computation power, it is impossible to simulate the entire phase 1 with enough resolution to capture the detailed fragmentation process. So currently, the link between phase 1 and phase 2 is still unclear. Therefore, previous studies have adopted simplified treatments for POP3 binaries. In previous studies, there are two main assumptions for POP3 binaries. The first is to assume that POP3 binaries are similar to their present-day counterparts. The second is to take POP3 protostar system from small-scale, high-resolution hydrodynamic simulations and turn them into POP3 clusters directly by boosting the masses of protostars. These two assumptions have one common problem, that is, they tend to overproduce closed binaries. Why? The reason is that, this is also mentioned by our last speaker, binaries of protostars tend to expand during accretion as the system gains angular momentum. So in light of this, we designed a new model to establish the link between phase 1 and phase 2. With this model, we can explore the dynamical evolution of POP3 clusters and also derive the binary statistics. Here is an overview of our approach. First, we generate initial conditions as the end products of phase 1 for such newly born POP3 clusters. Then we run pure n-body simulations for a sample of clusters from which we can derive the binary statistics. So the main advantage of our model is this initial condition model, which is the link between phase 1 and phase 2. So this model has three elements: global properties, initial mass function, and internal structure. For global properties, we make use of the scale-free nature of POP3 disk evolution. It is shown by self-similar transformation that the radius and mass of the system satisfy very simple parallel scaling relations with time. And also, with self-similar transformation, we can normalize the times in different simulations with different resolution according to the density threshold used to identify protostars or create sync particles. In this way, we can compare different simulations. And it is found by SUSA that the number of surviving fragments also follows a simple parallel. And it turns out that most small-scale simulations are consistent with one universal solution for POP3 disk evolution, shown here. With this universal solution, we can associate the global cluster properties at the end of phase 1 with two timescales. First, the fragmentation timescale tells us when the number of fragments is saturated. I'm talking about surviving fragments, not all fragments. And then the accretion timescale tells us the size and mass of the system when accretion is shut down by feedback. Note that this universal solution has captured the feature that the system can expand during accretion. Okay, here is a plot showing that how the universal solution feeds simulation data. Each data point is a set of simulations. And you can see the fit is pretty good. And we have typical scatters within a factor of 2, shown by the thin dashed lines. For the internal structure, we construct the newly born cluster as a hierarchy of binaries based on the properties of hierarchical fragmentation learned from small-scale simulations. The basic idea is that here I show you an example. These dots are stars. Each star is a node in this tree, and each connection between two stars tells us the relative locations of these two stars in a 60 phase space. And then in this way, we can generate the distributions of stars in this phase space. Okay, now let's look at the results. Let's start with our fiducial model. So in this fiducial model, the initial cluster size is about 0.15 per sec. And the total mass of stars is 400 solar masses. And the typical number of stars is 13. And this plot shows the distributions of 4 binary properties: the primary mass, separation, eccentricity, and mass ratio. And here, our results are denoted by the purple histograms. And we also show literature results with contours. Note that this solid contour is for protostars, not stars. That's why you can see it's like we have larger separations because that's protostars. The biggest difference between our results and those in previous studies is that we significantly underpredict or the fraction of stars in closed binaries with separations smaller than 100 AU. It's like this area. Another interesting findings are we found that the distributions of eccentricity and mass ratio are almost uniform. The results from other simulations with different parameters are similar as long as they follow the universal solution. Next, let's look at how the binary statistics depend on model parameters, especially for those extreme cases in which the universal solution does not hold. It turns out the most important parameter is cluster size. And besides, internal structure and stellar collisions are also important to some degree, but the most important thing is cluster size. So here I have a very busy plot, and it shows how many properties of binaries and clusters depend on the initial cluster size. In these models, I have fixed all the other parameters to the fiducial values, and I only changed the initial cluster size. Let's just focus on one quantity on the top right here, and this is the median separation. Here is the zoom in to that panel. Here we have a solid curve and a dashed curve. These two curves are from our models. And the solid curve shows the results for all binaries, including the binaries in quadruple and triple systems. And the dashed curve shows the results for isolated binaries only. And literature results are shown with horizontal lines. And on the larger end, you can see actually 3 data points at 1 radius. These are 3 different implementations of the internal structure. And on the lower, smaller end, you can see 2 data points. And for this lower one, we have reduced or surprised stellar collisions. As you can see, the median separation is almost proportional to the initial cluster size when we ignore stellar collisions. Interestingly, we can also reproduce literature results if we set the initial cluster size to exactly what they adopted, shown by these right regions. Finally, I would like to talk about some implications of our results. This plot shows the comoving density of accreted mass in POP3 black holes. The solid curve here shows the accretion from the ASM derived from cosmological simulation. The long dashed curve here shows an example for accretion in POP3 Xray binaries assumed in previous studies, which is pretty high. And all the other curves are the results for Xray binaries from our models. And you can see, and also this shaded region is the amount of accretion needed to explain the observed Xray background. So of course, the biggest finding is that we predict that the accretion of Xray binaries is actually pretty low. It's much lower than assumed in previous studies by about 4 orders of magnitude. And also this accretion in Xray binaries is actually overwhelmed by accretion from ASM, except for very early times, above, say, redshift 12. So the reason is that in our simulations, the efficiency of forming Xray binaries are actually very low. We can form 1 Xray binary in only every 10 to 100,000 solar masses. And also, most of our Xray binaries, they are only active at the gent phase of the donor star with very short lifetimes and little accretion. In summary, we found that binary statistics are highly sensitive to the initial cluster size. If we set the cluster size to what is expected from the universal solution, our models predict that the fractions of stars in closed binaries are actually much fewer than assumed in previous studies. As a result, we also have very low efficiency of forming Xray binaries. Therefore, we conclude that the feedback from POP3 Xray binaries is likely unimportant for the global evolution of the AGM, although they could be important if locally if they are formed. At last, I would like to share my outlook to future studies. First, to go deeper, we need to establish the link between phase 1 and phase 2 with more advanced simulations. We need to run the simulations longer with higher resolution. And to go broader, we need systematic investigations for the environments of POP3 star formation, such that we can evaluate how the outliers of the universal solution contribute to the overall properties of POP3 binaries. Last, finally, as our models show that closed binaries are probably rare in POP3 stars, then it's important to consider each statute channels for the formation and evolution of POP3 black hole binaries, such as dynamical capture of black holes and also three-body interactions with surrounding low mass stars in dense star clusters. For example, our binary statistics have been applied to explain one recent reported merger event detected by LEGO. This event is GW190521. This event is really interesting because it has two black holes in the classical mass gap of positional parents to be supernova. So it is really difficult to explain this event with classical binary evolution models for POP1 and POP2 stars. But POP3 stars are interesting or promising progenitors for such black holes. This plot shows the merger rate densities of such events similar to this event from many different models based on our binary statistics, considering isolated evolution and also environmental effects. And you can see these models have good agreement with the observed rate, which is shown by the shaded region. I think that's the end of my talk. Okay, thanks for your attention and feel free to ask me questions.
Thank you, Boyuan. That was a very nice talk. We have questions on the Slack. So, for example, Stefan is asking, for the initial conditions of the n-body simulations, how do you distribute the stars in phase space, and how long do you run the simulations for?
Okay, that's a good question. So we have learned from small-scale simulations that fragments are formed around persisting fragments instead of all around the central massive fragment. So that's why we construct this as a hierarchy of binaries. It's like each star is connected with another star as like in the form of a binary or pair. And then we generate binary properties or parameters for these pairs. And then once say we know the separation and we know the masses of two stars, then we can generate the velocities. And also we assume that they are all distributed in a disk with some scatters, vertical scatters. Yeah, that's the basic idea. Is every star is connected with another star. That's how we generate the initial condition for the distribution in a 60 phase space.
Awesome. You just answered one of the other questions as well. And as a last question, can you explain why you don't find a compact, smaller than 1 astronomical unit binaries?
Well,
why do you have this gap?
I think it's just because of the cluster size. We in our case, the initial size of the cluster is much bigger than assumed in previous studies, and also this also depends on how we implement internal structure, and we have shown that if we have implementation that is biased towards closed binaries, we can enhance the fraction of stars in closed binaries, but not much. It's still difficult to form closed binaries, especially for massive stars, because they will, to be massive, they need much accretion, and during accretion they will expand if we cannot efficiently transport angular momentum away. But these are all based on the universal solution. It's possible that in some cases, or maybe in most cases, the universal solution doesn't hold, because this is learned from our simulations and not constrained by observation. And it's possible that, say, we have some mechanism to transport angular momentum away, and in reality the cluster is smaller, then we can have more closed binaries. But we still don't know now.
Okay, thank you so much, Boyuan. And with that, please also check out Slack.
Thank you.
And let's move on to Nina, who will talk about population 3 star Xray binary feedback. Thank you.
Thank you, Anna. Just give me 1 second here. Okay. Okay, can everybody see my screen and hear me? Yeah, cool. Okay, well, first I would like to thank Anna and the other organizers for giving me the opportunity to speak. My name is Nina Sartorio. I'm a postdoc at University of Cambridge, and today I'm going to be talking a little bit about POP3 Xray binaries. So first I want to talk a little bit about Xray feedback. So how does Xray feedback affect the early universe? Why is it important? Well, it affects the early universe in mainly two frontiers. Two fronts. The first one is star formation. So X-rays, they have very long mean free paths. That means that if you have a mini halo that has an X-ray source, usually these X-rays are going to be able to travel long distances, maybe to the neighboring mini halos, and start doing damage there. And when they get to this neighboring mini halo, they can start either kicking electrons out of hydrogen atoms or ionizing them, and they increase the number of free electrons in the gas. Now, these free electrons, they can act as catalysts to induce H2 production. And as we know, H2 is one of the main coolants in early star formation. So it acts as a it counteracts the Lyman-Werner radiation effect, if you will. So Lyman-Werner radiation destroys H2, and in a way, X-rays, the more X-rays you have, the more H2 you can actually form as well. So depending on how many X-rays you have in comparison to Lyman-Werner, you might have either a boost in star formation or completely wipe it out. The other reason X-rays are important is because they affect the IgM. So they start heating and ionizing the IgM way before the UV from this initial POP3 stars can get there. And as it was mentioned before, this also affects the shape of the 21 centimeter line of hydrogen. And if you've seen the EDGE results, and if you believe them, which is two different things, then we might need a very early source of heating for the IgM. And X-rays is one of the ways that you could maybe start, walking towards that direction. So if you look at X-ray feedback today, there are two main culprits. So there are AGN and there are XRBs. So those are the X-ray binaries. And AGN today, they dominate. But if you look back, AGN requires supermassive black holes, and supermassive black holes require time to form. So even if you have black holes that form from the first POP3 stars that are more massive, or if you get direct collapse black holes, or even if you get a lot of mergers of protogalaxies, you still need time for those black holes to grow via accretion and via mergers to become the supermassive black holes we need for AGN. So what we usually expect is that AGN are not going to have that much effect in terms of X-ray production at redshifts much higher than 10. So after redshift 10, we expect that X-ray binaries are going to be the main producers in terms of X-rays. So AGN is out of the picture. Let's concentrate on the X-ray binaries. So first we have to say, well, can POP3 binaries form? Well, the general consensus is yes, as long as you don't have a huge amount of Lyman-Werner background, you're gonna get a lot of fragmentation on your disk, and you're gonna get multiple systems, and very often you're gonna get binaries. So this is something that has changed from the beginning of this research in the field, but in the last 10 years, a lot of simulations have shown that is actually probably the case. And what do these POP3 stars binaries look like? Well, it depends. It depends on a lot of things. So there's this plot that Tilman already showed, and I actually saw it the first time from Hirano in the conference earlier this year. So I apologize because I don't know who to thank for that. But you can see that there's a lot of a lot of dispute on what is actually the IMF, what is the range of masses for those stars. And if you believe our colleagues here, then we also have a distribution, thanks to Tilman's pool. But what is the fraction of stars that become black holes and neutron stars? Obviously depend on how many massive stars you have, and also how long they can survive in a system. So if you have a binary system and you have very massive stars, then those stars are not going to live as long. So that's also going to affect the X-ray feedback that you get. And also you have to think about orbital parameters. As we just heard, it's important to have closed binaries, because closed binaries is very easy for the black hole or the neutron star to just suck material out of its companion. But you also have to think about things like the eccentricity of the orbit. So I'm gonna talk a little bit about our work. So you already saw Tilman talk a little bit about A-sloth. So we actually use A-sloth, which maybe is not the best acronym, as Tilman said, but it definitely is the cutest symbol for a code that I've ever seen. And from that, we actually get a catalog of binary stars, which we, for every single redshift, so for POP3 binary stars. And we feed that in to another code called Binary C. Binary C is a population synthesis code. And we have been modifying it to include POP3 stellar evolution according to MISA. So now we can do consistent zero metallicity evolution for stars up to 1,000 solar masses. So this is all very new things. So the pipeline works a little bit like this. So we have 3 catalogs that we came from A-sloth. So we have a low mass catalog that with masses from 0.8 to 250 solar masses with an IMF slope like saltpeter. We have a fiducial model that goes from 2 solar masses to 180 solar masses with a slope of 0.5. And we have a high mass IMF with minimum mass of 10 and maximum mass of 1,000. And we take each one of those, every single binary in each one of those, and we put them in binary C. And then binary C evolves each one of those binary pairs from their main sequence, until the death of both of the stars. So this is resolving the orbits, is resolving how the stars are evolving and everything. And then whenever we have one star transferring mass to the other, and this leading to X-ray emission, then we classify that binary as an X-ray binary. And for that, we also output the average luminosity of the X-ray binary, the binary properties at that time, and how much time it spends as an X-ray binary. So just giving us a few results. So here we are plotting the luminosity in X-rays from 2 to 10 keV in ergs per second per megaparsec cubed. So this is co-moving megaparsec, I should say, versus redshift. So here you can see all 3 of our IMFs. And what you can see here is that the fiducial IMF is actually the one that gives the highest luminosity for X-rays. Especially at higher redshifts. The lower redshifts, it doesn't matter as much. And then followed by the low mass one, and then followed by the high mass one. Now, the blue dotted line here is actually the point where POP2 stars start outnumbering POP3 stars. And the dashed yellow line here shows that everything to the left, actually we expect AGN to dominate already the X-ray production. So in the early universe, you actually have quite a difference in how much X-rays you would expect of orders of magnitude, depending on the IMF you are using. Now, why does the fiducial IMF, which is the one that's kind of in the middle, right, is not the one with least massive stars, not the one with most massive stars, gives the most X-ray luminosity? Well, we have to look a little bit back from where we start. So if we take all the binaries from the catalogs before we fed them into binary C, the high mass IMF is the one with least binaries, because you're forming more massive stars, right? If you have a certain amount of stars to form stars, then you're going to be able to form less binaries overall. Followed then by the fiducial one, then followed by the low mass one. So you see that the low mass one, you have 205 million stars that we have of binaries. Now, the fiducia one and the high mass one have a much higher percentage of those stars that actually become XRB. So those are around 10% that we get. Whereas for the low mass case, we actually get a much lower binary X-ray binary fraction, right? So how does that come about? First, is because if you have more massive binaries, then it's going to determine how much time you can spend as an X-ray binary. So if here you see we are plotting the time that the binary spends emitting X-rays versus the luminosity. So you can see that both and the color code is the mass of the binary. So you can see that both for low mass, less massive binaries and more massive binaries, they spend quite a range of luminosities, but the higher mass binaries, they tend to emit for a lot less time. That's just because the star that is transferring mass is going to die very soon, or it's not going to stay on that evolutionary state for very long. So it just dies quickly. So it emits for less than a million years. Whereas the low mass ones, they start dominating in terms of they can be there for 1, 10, and even 1,000 million years, constantly giving X-ray feedback. So it's a bit of a play, as if you're massive enough, you're going to form more X-rays, right? If you more black holes and neutron stars, so you're going to have a higher fraction of X-ray binaries, but at the same time, you're going to be spending less time as an X-ray binary, even if you do form them. And I also wanted to highlight that it does matter about taking into account not only the separation of the binary, but also the eccentricity. So here we are plotting what we get in terms of X-ray. So here we're plotting eccentricity versus the separation. So the separation here, pay attention, is in solar radii. So if you don't know how to convert, this is like a cheat. So what you can see here is that even if you have fairly high separations of, 1,000 AU or so, you can still get X-ray binaries as long as you have a very high eccentricity. So here, the color shows the counts, how many cases you had of binaries being in that region, right? So you can see that here you actually have a fair number of binaries that actually are emitting X-rays, but they are very, very eccentric. So what's happening there is that instead of having a binary that's being constantly fed, is a binary that is getting material from its companion every time the companion reaches periastrum. So when they are very close together, the material is able to be sent. So this is my conclusions. And so in a nutshell, X-ray feedback in the early universe depends on a balance of compact objects and stellar lifetime. More top-heavy IMFs is going to produce more neutron stars and black holes, but is going to spend less time emitting X-rays. Neither a very top-heavy nor a very bottom-heavy IMF maximizes X-ray production. And X-ray feedback can still be produced at relatively high separations as long as there is also high eccentricity. And I stand there for questions. Thank you.
Thanks a lot, Nina. That was a very, very nice talk. We have questions already. Let me open the right Slack. Yeah. So again, Chiaki is asking how can X-rays or X-ray binaries contribute to cosmic reionization? Do they contribute?
So as I was saying in the first slide, so basically what you can think about is that most people think about that Swiss cheese model of reionization, right? So you have your little mini halos, and then they are producing UV, and then that bubble of UV starts expanding until all of them merge, and then you have a reionized IgM. But in reality, X-rays are going to start acting on the IgM early on. How much of this IgM the X-ray is going to be able to ionize is most likely not a very large fraction. It's going to be something like being, on the high end about 12, maybe very pushing it 15%, but most likely like about 7% or so. So, and it's gonna depend on how many X-rays we can really produce at the early universe, right? So if it is X-ray from X-ray binaries, then it's gonna depend on the IMF, like I showed here. I think one of the interesting things is that because it affects very strongly the shape of the 21 centimeter line, and that links so well to star formation, maybe one day by measuring the 21 centimeter line accurately, we're gonna be able to rule out models of what is producing X-rays, and they maybe even have some hints about what is the IMF from POP3 stars. So I hope that answers the question.
Okay, great. I have one more for you before we continue. From Kirk, who's more interested in the AGN version. Can massive black hole seeds cause a more local X-ray background that induces star formation within a galaxy?
Well, if you have a small black hole in the early universe, it definitely can accrete and it can emit X-rays if it's accreting. In a way, an X-ray binary is just a case of that when you actually have a binary star as being the feeder of the material. So possibly yes, but you know, you would have enough binaries, I hope, so that they would have a more significant effect than a solitary black hole that is trying to find something to accrete from, if that makes sense.
Okay, thank you, Nina.
Thank
and
you
also, you have more questions on Slack. And let's move on to the last speaker of the session. And after that, we would actually like to take a group picture. So I'll say it again later, but like be prepared to maybe turn on your camera for a moment so we can take a nice Slack Zoom overview picture. But now let's hear from Gen Chiaki on a triggered star formation by population 3-star supernovae. Take it away, please.
Okay, can you hear me? Good. Okay, so thank you for organizing this conference, Anna, and thank you for giving me the chance to talk today. Okay, so today I talk about the triggered star formation by POP3 supernovae. I'm Gen Chiaki in Georgia Tech, and my collaborator is John Weiss, Corey Brammer-Smith in Georgia Tech and Italian groups. Okay, so my research interest is to study the transition from POP3 to POP2 stars. POP3 stars form in mini halo with masses of 10 to 5 to 10 to 6 solar masses, and it can explode as supernovae and enrich the interstellar medium with metals and dust. Then in this enriched cloud, POP2 stars form. I want to study this process of enrichment. Okay, in previous study, I studied about the single enrichment event. So that means the enrichment from a single POP3 supernova with different types of supernovae, normal core collapse supernova and faint supernovae with different progenitor masses. In this case, I focused on the single enrichment, so the box size was small, 300 co-moving kilo/6. Then this result is press released on Texas University computing system. I really appreciate about this offer. And I can compare my results with the elemental abundances of observed EMP stars. The large symbols show my numerical result. It is the elemental abundances of enriched clouds. And the small dots show the distribution of observed EMP stars. For normal core collapse supernova case, it's a black square. We can see the elemental abundances is the mass range consistent with the range of the elemental abundances of observed carbon normal stars. This indicates that the single enrichment is enough to explain the formation of carbon normal stars. On the other hand, for the faint supernova models, the elemental abundances is less than the observed carbon-enhanced stars, such as Keras star, by several orders of magnitude. This indicates that the multi-enrichment events are required to explain the formation of carbon-enhanced stars. The opposite result is shown in the semi-analytic studies of Tilman Hartwig, 2018. So they predicted the carbon-enhanced stars are likely to form in mono-enriched region, whereas the carbon-normal stars are likely to form in the multi-enriched multi-enriched clouds. To clarify this, I ran simulation in the larger box size, 1 megaparsec. And today I show you the result of my test simulation, so with low resolution. But I expect that the result should be essentially the same as the higher resolution study. So I use the AMR code ENSO, and I use the chemistry and cooling library Glaco to solve the non-equilibrium chemistry for 48 chemical species, and I solved the 100 chemical reactions. Okay, so to study the multi-enrichment, I discretized the mass spectrum of population 3 stars into 6 mass bins. So in the intermediate mass regime, I assume that POP3 star explodes as faint supernovae, and the high mass regime, it explodes as pair instability supernova. So again, to reduce the numerical cost, I discretized the mass spectrum. So it's not that for example, the 33 solar mass and 65 solar mass stars explode, yield the same metal mass and amount of each element. Okay, this is the result of my simulation. So as the redshift decreases, the interstellar medium is enriched with metals and dust. I show the metallicity and dust to gas mass ratio. It increases around the supernovae. Okay, and other redshift for 17, this contour shows the metallicity, and the different color shows a different mass being. So in this most massive halo with 10 to 7 solar mass, the POP2 stars form, and the 3 POP3 supernovae contribute to the enrichment this cloud. So we can see the radial profile of metallicities from 10 solar mass faint supernovae and 33 and 65 faint supernovae. So 10 solar mass star can contribute to around 5 times 10 to minus 6 solar metallicity, and the other ones contribute around 10 to minus 3 solar metallicities. So interestingly, the elemental abundances of this cloud is very similar to the one of Keras star. So multi-enrichment is required to explain the formation of carbon-enhanced stars. And also interesting is this cloud can be plotted in the mono-enriched region, even though it is the multi-enriched. So yeah, it is a very interesting result. Okay, let me summarize my study. So I run simulations with large volume, 1 megaparsec. And so I can see the POP2 star formation in multi-enriched region. And next step is to run higher resolution simulation and to enlarge my simulation time to get the statistical samples of POP2 stars to compare with the large samples of observed EMP stars. Thank you so much.
Thank you very much. Thank you for so strictly sticking to your time limit as well. We have a first few questions on the Slack. For example, one by Tilman. is it you or the simulation who decide how many supernovae explode in one halo? So I guess that's the setup.
Okay, so now I assume the one single POP3 star in mini halo. But yeah, there is a room to improve this point. Yeah, thank you so much.
And then Rafael is asking, would you also like to focus on pair instability supernovae since they contribute maximum towards gas enrichment in nearby regions?
Okay, so in this case, I impose some random sampling for POP3 stellar mass with some log flat IMF. So this is I have only the 10 POP3 stars. So then the massive star that explode as pair instability is very rare. But if I extend the time of the simulation, I can see the pair instability supernova explosion, and then these explosive explosion can enrich the very nearby halos. So then, it is very interesting stuff.
And we have a further question from Mattis. Very nice talk, Jen. When you say the yeah, I agree. When you say the abundances are similar to the Keller star, are you referring only to the carbon and iron or all the elements?
Okay, I also follow all species from lithium to germanium, but I now show only the carbon and oxygen. And also in this talk, I show the magnesium to carbon ratio to compare to the Tilman's work. But I can follow all elements.
Okay, that sounds great. Thank you so much. And now I would say let's try to do a group picture. So if you could stop your sharing and everyone turn on their camera for a second. And I try to take as many screenshots as I can. Oh, awesome. 1 out of 6. And you can say 1, 2, 3 astronomy. And we get a smile. Awesome. I'm so happy about this great turnout and about the many great talks you're listening to. All right. Thank you so much. I'd say let's go for a short break. Please continue to check out the Slack channel. There's a lot of discussion going on there. If the speakers for the next sessions are awake already or still online, feel free to test out your presentations now, or let's do it the first 10 minutes before we reconvene at 15 past, and then Zoltan is going to take over the chairing from then. So thank you so much for this great first half of this conference. I loved all the talks. You are amazing speakers. Thank you.
I'm happy to share mine now. That's
okay. No. So.
Thank you for sharing.
Of course. Yeah.
Yeah, you're doing a really good job.
Thanks.
Anna, do you mind if I share my screen real quick?
Yeah, awesome. That would be great. I see it. I don't see the presentation mode yet.
Okay, so I'm going to try. Okay.
Oh, I love videos.
Yeah. Okay. I think platform. Yeah, that's right. Okay. Thank you.
Awesome. Thank you. Does anyone else of the second?
Also test my share screen. Yeah.
Okay, perfect.
Yeah.
Thank you.
Simon here, Simon Glover. You're the first speaker, so you could maybe try it.
Okay, Simon just messaged me. He'll test his at the end of the break.
Oh, okay.
Is it okay if I test mine now then?
Absolutely.
Okay. Is that okay?
Yes, I can see you and like your presentation in presentation mode.
Great.
Awesome.
Also, thank you for chairing this and organizing everything.
You're welcome. Sultan will actually be chairing your session, so. But yeah. Great.
So can I go ahead and check my next? Oh, sorry, you go first.
Okay. So can you see?
Yeah.
Yes, but I see like what you're probably supposed to see. So I see the first slide and the second slide.
Now?
Yes, yes.
Sorry, I have to check the video.
Oh, I like that.
Okay, it's good. Thank you.
Yeah, beautiful. Thank you.
So maybe I'll go now.
Please go ahead.
Hi, can I try to share to the screen?
Yeah,
Federica.
let's go with Eli first, and then let's do you.
Okay, thank you.
All right. Are
yes.
we successful? All right, thank you.
Perfect.
Can I try now? Can I
Yes.
try? Thank you.
Looks all good.
Thank you very much.
All right, and then Simon will just test his, like I think the last 10 minutes or so from the break. Okay. I will put up the information slide again and also like go for a quick coffee. Anything anyone would like to say or discuss, or Zoltan, do you have any questions?
You could teach me how to do the warning on the screen, the two minute left warning.
So I looked at the time and and I wrote myself like little notes, and then it's important because I have the green screen that I hold them up in front of me and not next to me, because then they disappear. Think if you can like write a 2 and a 1 and a 0 on a piece of paper and just hold it into the camera. I think that's good enough.
I thought there was a way to actually flash a thing on the
on
the screen. If you're the host, there's some annotation button. But...
Oh. I did it the old-fashioned way.
Actually, can you make me co-host?
Oh, you're not co-host? Okay, yeah, of course.
I will try.
I think you are. Are you maybe logged in from 2 different accounts?
It's okay, but usually an annotation button on the top.
I think the annotation feature in Zoom needs to be activated by the host before the meeting in like this online thing where we also created the call. So I don't know if it's worth fiddling around with this now.
Okay.
Yeah. I can quickly take a look at the Zoom webpage. Thanks, Tilman. Yeah, I can't change the properties on the current meeting. I'm sorry, Sultan.
No, that's fine.
I'm sorry. I didn't know this would exist in principle. So, all right.
See you in 20 minutes.
Yeah, I also turn in a little bit before, yeah. Let me share this. Perfect. See you in a bit.
Hi, Simon, are you around? Simon Glover?
Yep. Do you want me to share my presentation now?
Hi, how are you doing?
Good, good, thanks.
Yeah, why don't you share it so we can start on time?
Okay. Do you see that okay?
Actually, no, I still see Anna's slide. No, it's okay. I see it in, yeah, you want to do presentation mode? Yeah, looks good. Can you see that?
Yep.
All right, so I think we should try to start on time. Welcome back, everybody, except for we say good night to the folks on the east, and we say good morning to the folks on the west. So the second session will have 7 talks, 15 minutes each. And the first speaker is Simon Glover, who will tell us about H2 region trapping in POP3 accretion disks. Thanks, Simon. And I'll give warnings at 3 minutes and 1 minute.
Thank you, and thank you to the organizers for giving me the chance to talk about this today. So I want to start by thanking my collaborators, and in particular I want to highlight Andre Yara, because the work I'm going to be talking about today is basically the project that he carried out in the second half of his PhD thesis. So we've already heard quite a lot about POP3 star formation. I just want to take a minute or two to just remind everybody of what the kind of current consensus picture is. Basically, if we have a mini halo cooled just by H2, we know that it cools, collapses, but it doesn't cool as much as we would see in a normal GMC in the nearby universe. So the temperature remains reasonably high. And this high temperature implies a high mass inflow rate. So mass flows into the center of these objects at a much higher rate than is typical, again, in the local star formation. And this rapid inflow of mass, combined with the fact that you have non-zero angular momentum, builds up a massive POP3 accretion disk that becomes unstable and fragments. So we've seen a number of examples of this already. This is just another one from a recent paper by Katarina Wallenberg that I wanted to highlight. Now, there are some points of contention here, as we've already heard, mainly how many fragments form and what happens to them, how many of them actually merge with each other versus get ejected from the system. But I think there's general agreement that one or more of these fragments is going to survive down at the center of the halo, is going to accrete enough mass to become a massive star. And once this massive star or these massive stars, if you form more than one, contract to the main sequence, they're going to become sources of ionizing photons. And most of the previous numerical work on this, including some of the simulations we've heard about today, then find that the ionizing radiation produced by these massive stars escapes to large distances in the halo and ultimately shuts off accretion by shutting off the supply of gas to the disk and ultimately photoevaporating the disk. So this is kind of the consensus picture. So this is just an example from a paper from a few years ago by Stacy et al., where you can see the growth of these regions of ionized hydrogen as a function of time. Or there's another study from a few years ago by Takeshi Hosokawa, again, showing, first of all, the outbreak of a photodissociation region in the polar regions of the disk. And then this is followed later on, once the stars become more massive, by the outbreak of an H2 region, which ultimately photoionizes all of the gas and gets rid of the disk. Now, we wanted to investigate the impact of radiation on the disk in more detail. So what we did a couple of years ago was start carrying out a series of simulations of this using the repo moving mesh code. So the basic setup we're using here is we're starting with simplified initial conditions. We start with an unstable Born-Haber sphere with a mass of a few thousand solar masses, and the initial density at the center of a few times 10 to the 4 particles per centimeter cubed. We give it some initial rotation and a small level of turbulence, and then follow its gravitational collapse and see what happens. We're using the standard treatment of primordial cooling and chemistry. I can talk about these at great length if anybody's interested. And we're following the collapse until we get up to number densities of around 10 to the 14 particles per centimeter cubed, at which point we're replacing any regions that are still undergoing gravitational collapse using sync particles. Once we have sinks that have become sufficiently massive that we expect them to be sources of UV radiation, so once they get to masses of like 10, 20 solar masses, we then follow the propagation of UV radiation, both photodissociating radiation and ionizing radiation, around all of these sinks using the Xray algorithm. And I should stress we're actually following the radiation from all of the sources that we form in the simulation, not just the one central one. Now, thanks to the moving mesh nature of a repo and its high computational efficiency, we're able with these simulations to reach extremely high resolutions close to the sink. So we reach sub-AU spatial resolutions. So this is just an illustration of that. So once we get up to densities characteristic of the center of the accretion disk, the region around the sink particles, which is number densities of 10 to the 13, 10 to the 14 particles per centimeter cubed, we have sub-AU sized cells with typical masses of about 10 to the minus 5 solar masses all the way. So these are very high resolution simulations. So that's the basic setup. And since I only had a small amount of time, that's gone through that very quickly. But I'm happy to talk at greater length in the comments later about the details. So what did we find? Well, the big surprise that we found with these simulations, which in retrospect shouldn't have been a big surprise, is that ionizing radiation didn't seem to do anything. So here's an illustration of this. So this is the state of the simulation at the point where we have a massive binary. So two central stars, both of which have masses of around 30 or 40 solar masses. So these are bright sources of ionizing radiation. And yet when you look at the density distribution, when you look at the temperature distribution, there's no real impact of this ionizing radiation on the surrounding gas. So what's going on? Well, if we look at the actual chemical composition, we see that what's going on is the gas has remained mostly neutral. Within the disk, it's highly molecular, and the ionized gas is all trapped in the center of the disk. It's not broken out of the disk into the polar regions. It's just sitting down in the center, and it's unable to escape. So why does this happen? Why does the H2 region get trapped down in the center of the disk? Well, we've looked at this in some detail, and basically what's going on here is just that at these densities, the size of the Stromgren radius you create is very, very small. The typical disk densities are around 10 to the 13 to 10 to the 14 particles per centimeter cubed. At that density, your Stromgren radius obviously depends on your ionizing photon flux per second, but even for the most massive stars, your Stromgren radius is 0.1 of an AU or 0.01 of an AU. It's tiny. It's very close to the central star and much smaller than the scale height of the disk. The scale height of the disk in the central regions here is a few AU. So your initial ionized region is very small. And then if you look at the force balance, if you look at the forces acting on this ionized gas, so the radiation pressure force and the thermal pressure force trying to push it outwards, and the gravitational attraction of the gas and the star responsible for the ionization, you find that gravity wins. And this is illustrated in this plot. So the solid lines here are the gravitational attraction as a function of distance from the star for stars of several different masses. And also the blue line here is showing what happens if you don't have a star, if you just have the central gas. And then the dashed lines are how much combined radiation and thermal pressure is pushing outwards. So you see, if you didn't have the star there, then the pressure of the H2 region would dominate, the H2 region would expand, it would escape from the disk, no problem. But as soon as you actually put a central source there, its own gravity stops the H2 region from expanding. It traps it within the disk. The H2 region can't expand out of the disk because even though it's overpressured compared to its surroundings, it's trapped there by gravity. And I said at the start that this shouldn't have been a surprise. And the reason is we actually already have encountered this kind of behavior in simulations of massive star formation, but it's in simulations of present day massive star formation. So this is a known issue. The big difference with present day massive star formation, well, there's two of them. One is you have much more radiation pressure, so because you have dust, so it's much easier for even a moderately massive star to eventually reach the point where radiation pressure wins out over gravity. And secondly, you have much smaller typical mass inflow rates, mass accretion rates onto your stars. So again, it's easier for the effects of the ionization to overcome the effects of the inflow. But you do not have this in this case. Thank you. Oh, so what does this result depend on? Why do we find this behavior and everybody else finds something else? Well, this result depends crucially on two things. First, resolution. If you're not resolving the disk scale height, you're not going to see this behavior. And second, the treatment of the gas close to the star. So when we are using sync particles here, what we're doing is a kind of skimming technique. We put in a sync particle with some accretion radius. We don't take away all of the gas within that accretion radius. We remove the gas down to some threshold density so that the time step doesn't become impossibly small, but we don't remove all of the gas. So we don't create an artificial hole in the density distribution, as used to be the case when we were doing this with SPH. And this means that the setup allows us to inject the radiation at the actual location of the stellar surface. So on a sub-AU scale rather than at the boundary of the sink. And this makes a huge difference. If you put in the radiation at the edge of your sink and your sink is larger than the size of the disk, if it's larger than the scale height, then basically your sink pokes out of the disk. And if you do simulations with that setup, so here's an example where we deliberately used that approach, where we took a large sink radius and put in the radiation at the edge of the sink, then your H2 region can escape. Then it can escape into the polar regions and do all the usual things that we've seen already. So if the sink radius is bigger than the scale height and you put the radiation in at the edge of the sink rather than where the actual star actually is, then the radiation immediately escapes. But that's kind of by construction. You've chosen to inject the radiation into these regions that are already at low densities. If you don't do that, if you try and do something more physical, then you find that the radiation doesn't actually get out. So what does this mean? Are we claiming that all H2 regions are actually trapped in the disks and we never actually ionize the surrounding gas? I don't think we can make that claim yet for a couple of reasons. One, we need to run the simulations for much longer. With this set of simulations, we're able to follow the evolution for 20,000 years, but this is still a fairly small fraction of the lifetime of these stars. And you could imagine that at later times, if you have less gas being supplied to the disk, the densities drop and it becomes easier for the H2 regions to break out. That's unclear. We need to go on for much longer. Secondly, we're clearly missing some physics here. So one thing that we've already heard about is magnetic fields. If you can build up a strong magnetic field in the disk and drive a jet, that's going to punch holes in the disk, and that might allow radiation to escape. And the second important bit of missing physics, although we're treating the direct radiation pressure of the ionizing radiation, we're not treating the effects of Lyman alpha scattering, which potentially is going to give you a much larger radiation pressure while the H2 region remains trapped, because the photons just scatter backwards and forwards and contribute more than once to the actual total radiation pressure. So it could be that these effects, if we account for them, are actually going to allow the H2 regions to escape. So the real point to take away is, I think these simulations demonstrate we still don't have a good understanding of the early stages of growth of H2 regions around POP3 stars. We know what happens once you've escaped from the disk. We don't know how they get out of the disk. And they may become trapped in the disk for extended periods. And they also show that if you really want to simulate this, high resolution close to the star is vital. If you're not resolving the scale height of the accretion disk, if you're not resolving the gas distribution immediately around the massive stars, then you're actually going to get qualitatively different results from what you find if you do that. Yeah, and so if you take one thing away from this talk, it's that we really need extremely high resolution to model this process. And I don't think any simulations really are quite there yet. Thank you.
Great. Thanks, Simon, for finishing on time. And we have several questions on the Slack. I'm going to just read, I guess, them in order. So John Reagan asks, would we not have expected this from a simple cloudy calculation? Because in the SMS simulations, supermassive star simulations, with very large mass inflow, we have found something similar. Massive POP3 stars do not create large H2 regions. It's interesting that the results are similar, and it's good for growing stars.
We should have expected this from reading the present day massive star formation literature, but it's one of these cases you don't actually realize until you see it in your own simulations.
Actually, let me jump to one that Sugimura asked, which I wanted to ask myself, is are the protostars physically embedded within this, even very close to the protostars? And my version of the same question was, is the initial condition self-consistent in the sense that if you started to shine the UV light earlier, maybe you would not have built this dense disk very close to the star? So can you comment on that?
Well, you need that dense gas close to the star to build up the star in the first place. We're not plonking in the star with 20 or 30 solar masses. It's growing by accretion from its surroundings. And unless you have some physical mechanism for switching off that accretion, that gas is still going to be there. And what our simulations are showing is that the photoionization by itself is not sufficient for clearing out that gas in the immediate surroundings of the star. Now, it could be that the missing physics I've talked about, the Lyman alpha radiation pressure, or the magnetically driven jets can do that. But the ionizing radiation by itself can't.
So there was another one, I think last one by Jen Chiaki. Great result. If you could follow the radiation transfer for the whole time of the main sequence, can the H2 region eventually expand to the parsec scale as larger scale and low resolution simulations found in the past? I think you kind of answered this, but you want to say something else quick?
Yeah, I can't really answer that. I mean, I think once the H2 region manages to escape and start ionizing the surroundings of the disk, then things are going to proceed pretty much how we've seen them in previous simulations. But how long it takes to get to that point, I think we don't know. I think the real point to take away from this study is, yeah, we still don't know the answer to this question.
All right, stay tuned then. Thanks, Simon, again for great talk, very interesting result. So next talk is by Federica Sassano on the nature of the first supermassive black hole seeds.
Yes. Hi to everybody. Thank you for this opportunity. Can you hear me? Can you see my slide?
Perfect, thanks.
Thank you. So I'm Federica Sassano. I'm a PhD student at Sapienza University of Rome. I will talk about the nature of first supermassive black hole seeds. Recently, one of the most distant quasar has been detected at high redshift, at redshift 7.5. And it means that these supermassive black holes with typical masses of 10 to the 9 solar masses must have formed in less than 700 million years after the Big Bang. Currently, the existence of such massive black holes represent one of the most hot topics in astrophysics. If we take 5 of the most distant and massive supermassive black hole at high redshift, we can ask which is the typical mass expected for a single progenitor or a single black hole seed around the epoch of formation of first stars and black holes. It means around redshift 2030. If we assume an unimpeded Eddington accretion rate onto this seed, we can go backward in time and see that typically the mass expected for this black hole seed is expected to be 10 to the 4 or more. But this is a very optimistic assumption, both because actually we don't know the nature of these black hole seed progenitors, but we expect that a multiplicity of black hole seeds could have originated a supermassive black hole at high redshift, and both because we expect that these seeds in very gas-rich galaxies, which are at high redshift, could have accreted at super Eddington flows. In my talk, I will focus only on the nature of these black hole seeds progenitors. Theoretical work mainly suggests that 3 kinds of black hole seeds can exist in nature, among which light seeds, which have typical masses of around 100 solar masses, which can form from the collapse of pop-3 stars, which can form in those environments where H2 cooling is available. The main qualities that this environment must have, we need as first that Lyman-Werner radiation from the background must be under a certain critical threshold, and in order of not ferment the H2. And we need that the lack of metals and lack of dust to gas maceration. If one of these properties is present, we need that this must be under a certain critical threshold. In more massive halos, if we have a certain amount of Lyman-Werner radiation, and if this is over a certain critical threshold, we can have the direct collapse of a cloud, which leads to the formation of a supermassive star, which can continue to gain mass from the hot envelope, leading to the formation of a heavy seed with typical masses of around 10 to the 5 solar masses. In the same kind of environment, if we have a certain amount of dust to gas mass ratio, we can have the formation of a dense stellar cluster, because dust is able to ferment gas to high densities. Hence, we can have some stellar runaway collisions which lead to the formation of a medium weight seed with typically 10 to the 3 solar masses. Once we know the condition that lead to the formation of each channel, we can follow their formation in high redshift galaxies and their connection and their involvement in the formation of a supermassive black hole at redshift 6. To this aim, I've adopted a semi-analytic model, gamete equation of dust, which is able to reconstruct the dark matter halo major tree of a quasar host. And in particular, we are talking about a dark matter halo of mass typically of 10 to the 13 solar masses, an extremely biased region of the universe. Once we are able to reconstruct the major tree, this code is able to follow star formation, chemical evolution, black hole seeding, feedback, and so on. In this model, we have implemented a homogeneous treatment for metal diffusion, which is a highly homogeneous process, in particular at high redshift, and Lyman-Werner background fluctuation. This because it is well known that these fluctuations are tightly connected to potential hosts of medium weight and heavy seeds. These are the critical thresholds we have adopted in order to to see where the critical threshold adopted inside our model. And we have run 2 different simulations adopting 2 different models, 2 different critical thresholds for the Lyman-Werner background of 300 and 1000. Now I want to show you our results, the redshift distribution for light, medium weight, and heavy seeds, adopting a critical threshold of 300. And each panel shows 2 different histograms. The lighter ones are all black hole seeds that we can form in our simulation. And the darker ones represent only those black holes that merge to form the supermassive black hole. It means only black hole progenitors. We can see that light seeds start to form early down to redshift 19, when the increase of the Lyman-Werner background radiation suppress POP3 star formation, while heavy seeds and medium weight seeds continues to form down to redshift 15, where all seeds stop to form due to the metal enrichment. It means that all the volume of the simulation is filled by metals. In particular, if we focus only on the darker one, we can follow it means the progenitors, we can follow evolution of the total nuclear black hole mass as function of redshift, which is the black solid line. The gray area represents the minimum and the maximum of the mass available at each redshift. And the colored lines represent different contributions coming from heavy, medium weight, and light seeds. We can see that at very high redshift, above redshift 20, light seeds dominates on the total mass. Once heavy seeds start to form at redshift 20 down to 16, we observe that heavy seeds dominates on the total mass, while below redshift 16, only when all seeds stop to form, only thanks to accretion we can reach the final mass of the supermassive black holes. Medium weight seeds is important to stress that are always subdominant. By increasing the critical threshold of the Lyman-Werner radiation to 1000, we observe an increase in the total number of light seeds that we can form in our simulation. And this is due to the fact that we are increasing the star formation efficiency, and we observed a decrease in the total number of medium weight and heavy seeds which can form. This is due to both to the higher critical threshold for the Lyman-Werner radiation, but also to a more efficient metal enrichment. Now, recently a new work was released by Chone Onomukai, where they have studied the impact of metallicity on accretion onto supermassive star. And they have observed that for very low metallicity and high metallicity down to 10 to the minus 4, thanks to the higher accretion rates, supermassive star can still gain enough mass in order to reproduce a heavy seed. And the same can be inferred for a medium weight seed, which can still form for metallicity of 10 to the minus 3. So I've taken the results, which implies a wider range in metallicity where they can form heavier seeds. And I've run 2 different models adopting these 2 quantities of the critical Lyman-Werner radiation. I labeled this SKA as super competitive accretion. And I want you to show the comparison with our model. We observe an increase in the total number of seeds which now can form. This is due to the more favorable black hole seeding conditions, but we observe a decrease in the total number of heavy seeds which can form in the model SKA 1000. To understand why, now let's see the implication on the total evolution of the nuclear black hole mass. Despite the larger number of seeds which can form, in SKA 300 model, we can still reproduce, and the evolution is similar to the previous case, and we reproduce the final mass of the supermassive black hole. But in SKA 1000, we observe that the final mass of the supermassive black hole is not reproduced. In this model, we observe that medium weight seeds are comparable in mass to the heavy seed one. And to understand which is the implication, I need you to show the black hole mass function at redshift 15. It means when all seeds stop to form. The average black hole seed mass is the vertical line. In this plot, I show the different models I showed you before. And vertical lines show the average black hole seed mass. It means the average black hole that we have at the last epoch of seeding formation. We observe that in SKA 1000, this is the lowest value. And this means that quality but not quantity is an important parameter in order to establish if the final mass of the supermassive black hole is reproduced. Finally, in this work, we have addressed the formation and evolution of 3 different black hole seed populations within a self-consistent cosmological model. And these black hole seed populations are strongly connected to each other. We observe that heavy seeds provide the dominant mass and contribution, and that quality but not quantity is a key parameter to establish if the final mass of the supermassive black hole is reproduced. Also, if black hole progenitor represent only the 10 or 20% of all black hole seed population, also the satellites can provide a catalog of black binary systems detectable with the 3rd generation GW telescopes. Thank you.
Thank you for a nice talk. We have a couple of questions on the Slack. So first question is about mergers. Could you clarify what role did the massive black hole mergers play in the model?
Okay, so you mean, as you can see, merger can play an important but not dominant role, because the dominant role is accretion. But merger can be important at very high redshift, because if we reproduce a massive black hole above redshift 15, this can be very important to define the the following evolution of the nuclear black hole. So we observe that accretion is the most important parameter despite merger.
The second question is the number of black hole seeds in your model consistent with the number of observed quasars?
So quasars are is the final mass that you want to reproduce. Actually, we are defining seed at very high redshift, and you cannot detect them, or until now you cannot detect them. In the future, we hope it will be possible with 3rd generation GW telescopes, but the aim is opposite. It means we take the observed supermassive black holes and we want to reproduce them by making some history of seeds. So it's something that you want to reproduce. Is this the first objective?
Yes, I think, yeah. I think you basically modeled the history of a single quasar, as far as I understand.
Yes, yes.
So, okay, last question is actually from Boyuan and myself. I think it's very similar. How did you handle the spatial distribution of halos? It was not actually clear to me if you used Millennium simulation or just a semi-analytic model. And in any case, the small halos are unresolved. So how do you handle the spatial distribution and also the inhomogeneous metal enrichment?
So we don't resolve spatial resolution, but we adopt a percent sector in order to reproduce the number of halo and their mass in our comoving volume. But in order to reproduce inhomogeneous quantities, we have adopted, for the metallicity, a filling factor, where we are assuming that supernova bubbles, that we know how many supernova bubbles we have in each halo, are expanding. And we compute at each redshift the volume filling factor, and we define a probability of a single, for a single halo to take from the AGM a certain amount of enriched medium. And for the Lyman-Werner radiation, we are adopting a non-bias. We also define a probability to find in the proximity of a certain halo as function of redshift, mass of the first halo, second halo, which is the probability to find a star-forming region in the nearby, according to the work of Dijkstra, Iliev, and so on. So we adopt probability.
Okay, but effectively, the halos are randomly distributed. The clustering is not modeled this. Is that correct?
In which, no, can you repeat?
Okay, maybe I'll do it on Slack later because I think.
Okay, thank you.
Okay, I will move to Slack. So thanks again, Federica. Nice talk. Next talk is by Eli Visbal, who will talk about the impact of feedback processes on POP3 star formation.
All right, let me.
Thanks, Eli.
Okay, can we see my slides?
Yeah.
Okay. Thank you very much to the organizers. This is a really wonderful conference so far. For anyone who doesn't know me, my name is Eli Visbal. I'm an assistant professor at the University of Toledo. Today I'm going to discuss some work I've recently completed with Greg Bryan and Zoltan on using semi-analytic models to understand how feedback processes affect population 3 star formation. So I want to begin just with a motivation for using semi-analytic models as a computational approach. We've heard a lot today about, well, some about semi-analytics, but also a lot about hydrodynamical cosmological simulations. These are a very important tool to understand the formation of the first stars and galaxies, in particular because they can have a very detailed, sophisticated treatment of of many important physical processes, such as the chemistry of primordial gas, cooling, collapse of gas, even radiative transfer of ionizing radiation through the intergalactic medium. The main disadvantage of simulations, though, is that they're computationally expensive. For instance, the Renaissance simulations, we have a figure on the right here from this suite of simulations, took millions of CPU hours to run. And because of this expense, it restricts the amount of volume, cosmological volume, or redshift range we can cover when performing these simulations. And even though the treatment of physics is very sophisticated, some subgrid physics is still required, and this leaves us with free parameters. For instance, the initial mass functions of POP3 or POP2 stars, or in some simulations, the transition from the critical metallicity for the transition from POP3 to metal-enriched star formation. And so it can be challenging to explore the entire parameter space of this physics in the high redshift universe with just hydro simulations alone. So it's complementary if we also have fast alternative approaches, and semi-analytics fits that description. So I'm going to describe a model we've recently put out. It is based on cosmological n-body simulations. And so we extract merger trees and, importantly, the three-dimensional positions of the halos in the simulations. So we actually do include the full clustering of all the halos in our semi-analytic model. Once we have these positions and merger trees for the dark matter halos, we can apply analytic prescriptions to determine where POP3 stars form, as well as where the first galaxies and metal-enriched star formation occurs. And so we include the important processes for POP3 star formation, including H2 photodissociation due to Lyman-Werner radiation. We include metal enrichment, like we just discussed in the previous question and answer from the previous excellent talk. But here we actually include external metal enrichment bubbles and the clustering of nearby halos, how one galaxy or cluster of POP3 stars in one halo can pollute with supernovae winds nearby halos with metals. We also include the homogeneous ionization of the intergalactic medium. And finally, we include the baryon-dark streaming velocity. So these are very computationally efficient. They run quickly on one core. Here is just a snapshot of one of our models. In a 5 megaparsec box, we have on the left all of these are the halos above 10 to the 6 solar masses. And then on the right, we show which halos are either hosting population 3 or metal enriched star formation. All right, so I don't have time to discuss all of the details of the physical prescriptions we put in the models, but I just wanted to mention briefly how we handle these three-dimensional clustering effects. So we've developed a new grid-based method where essentially we distribute all of the halos in our simulation box on a grid. And this allows us to use essentially the convolution theorem and fast Fourier transforms to quickly compute the feedback processes that depend on the separations between various halos, including Lyman-Werner feedback, external metal enrichment, and reionization. And so this allows us to figure out which halos should be hosting POP3 versus metal-enriched star formation. And so here are some projections from one of our simulation boxes. It's a 3 megaparsec box at redshift 8.6. On the left, we see which halos are hosting POP3 versus metal-enriched star formation. In the center panel, we see the metal bubbles due to supernovae winds that have propagated throughout the intergalactic medium. And so this is the projection of parts of the simulation that are enriched sufficiently that you would have POP2 and no longer have POP3 star formation. And then on the right, we show the projection of the reionization bubbles at the same redshift, which also impacts where stars can form because reionization photoheats the gas and can make it hard to form stars in small dark matter halos. Okay, so because this model is very computationally efficient, we went through and explored the parameter space to determine how different physics affects mainly the star formation rate density, both in population 3 stars and metal enriched stars. And so we can both check how different model parameters affect these quantities, as well as turning off various feedback prescriptions one by one to see how things build up to create the final star formation rate densities we see in our models. So here I plotted the star formation rate density as a function of redshift, both for population 3 in the lower curves and metal enriched. This is a case where we varied the star formation efficiency in population 3 star forming halos. And so this is just one example of varying one of the parameters in our model. But I just wanted to, at first, just go over some of the broad brushstroke results we see. Generally, we see a transition from POP3 to metal-enriched star formation quite early on in our simulations. The exact redshift of this transition depends on the precise prescription, but it happens very early always. And then another thing we see is most of our models see persistent population 3 star formation to the end of our simulations at redshift 6. And so I'd say this is an important takeaway result. I'd also say that following the 3D clustering of halos and their spatial distributions seems to be particularly important below a redshift of about 15. And this is because at higher redshifts, the metal bubbles in our prescription, as well as the reionization bubbles, are so small that even with the bias clustering of halos, we don't, the spatial positions of the halos make less of a difference. Okay, so I just want to then show a couple more results from our models. So let's start with external metal enrichment. We have a relatively simple prescription. We assume that after stars form, supernovae push metal bubbles out with a constant velocity up to some maximum radius. Then we have a free parameter that allows us to vary the size of these bubbles. And we also have a free parameter for the critical metallicity, where you have a transition from POP3 to metal-enriched star formation. And so here I plotted the POP3 star formation rate density and metal-enriched for varying these different parameters. And we can see that in our fiducial model, we have this persistent population 3 star formation down to redshift 6. But if you increase the size of the bubbles by a factor of 2 and reduce the critical metallicity, you can really begin to quench POP3 star formation at this redshift of 6. So we believe that there's likely to be this persistent POP3, but it is sensitive to the details of external metal enrichment. the one last, so I don't have time to go over very many of our results, but the last one I'm going to summarize is the impact of reionization. So as I mentioned, ionization photoheats gas. It increases the minimum mass of halos that can form stars efficiently. And so we've looked at how this affects the star formation rate density in our model. Here we've plotted our fiducial model, and then for comparison in red, a case where the escape fractions are reduced by a factor of 3. So this would basically be if reionization happened much more slowly and was much weaker, we can just ask what would happen in that case. And we found it quite surprising initially that it didn't seem to change the star formation rate density in our simulation. But when we went and looked at individual halos, we were able to understand what was happening much better. So here are plots showing individual POP3 star formation events in our fiducial model, as well as the case where we've weakened reionization. And so this shows the mass of a halo where POP3 stars form is a function of redshift. And it turns out that the total POP3 star formation is similar in both of these runs, but the main difference is where the POP3 star formation occurs. So when you turn off, or when you turn down reionization, lower the escape fraction, you have very few regions that are ionized. So you get most of the star formation occurs at the atomic cooling limit, which is this dashed curve. You have fewer halos where star formation is suppressed all the way up to this higher mass, which is what we've assumed for the minimum mass in an ionized portion of the intergalactic medium. And so this was an interesting observation, and it mainly has to do with our assumptions about having a constant star formation efficiency in all of our halos, as well as the shape of the halo mass function. And another sort of broad point that this makes for us is that that as we march from the very early universe down through the epoch of reionization, it should be generically true, and as we know, that we should transition from POP3 star formation mainly being in mini halos to either atomic cooling halos or pristine halos that were ionized and then collapse, and star formation occurs in even more massive halos than the atomic cooling limit. And so I think this type of result motivates additional simulations for these sort of lower redshift POP3 star formation in either atomic cooling halos or even more massive halos. So we looked at other physics such as supernovae feedback. I'm running out of time, but I'll just point out that we assume the metal-enriched star formation occurs in a halo after POP3 with some delay due to having to recover from a supernovae explosion. And we find that when you change this delay time, you can very dramatically shift when you get a transition from metal-enriched dominating, which is these top curves, rather than metal-enriched dominating at very early redshifts. It can move to lower redshifts when metal-enriched star formation dominates over the population 3. So that brings me to the end of this presentation. I think I'm out of time exactly, so I will leave my summary and conclusions up here. But the one thing I did want to say is I wanted to advertise a postdoctoral position. I'm hoping to hire a postdoc at the University of Toledo starting next fall to work on topics related to the high redshift universe, including possible topics could include the first stars, first supermassive black holes, or studying the new technique of measuring the large-scale structure in line emission with galaxy line intensity mapping. So I'd encourage anyone who's on the job market or knows anyone to keep an eye out for this ad, which will appear on the job register next week. So thank you very much.
Thank you, Eli, for a nice talk. Actually, you stimulated a very large number of questions on Slack. So I think I'm just going to ask one of them, and then you're encouraged to answer them on Slack. The question asked by Rafael Schneider is, Well, nice work. Your POP3 star formation rate density at redshift below 6 seems to flatten. Why is the star formation rate density in POP3 stars not dropping due to reionization?
So essentially what happens, so the reason why we maintain a flat star formation rate density is that we essentially have halos that are below this critical metallicity down to, so pristine, or even if they're not pristine, low metallicity halos that are low enough below the threshold we've set. And so really you essentially, a generic thing we generally find is reionization bubbles are larger than the metal bubbles for our for what we thought was a realistic prescription. And you'll reionize pristine halos, delay the star formation, and then depending on how big the metal bubbles are and the threshold for transitioning from POP3 to POP2, either those metals will catch up with and essentially pollute before star formation can occur. But if, depending on the exact values of those parameters we put, if the metal bubbles don't expand far enough, you'll still be able to make POP3 stars in those pristine massive halos where reionization delayed star formation, but eventually the halo gets big enough that it does make POP3 stars.
Okay, thanks, Eli. So please answer the rest on Slack.
Okay, thank you.
The next talk is by Mihir Kulkarni, who will tell us about his work on the critical halo mass for POP3 star formation and how this depends on Lyman-Werner radiation, baryon streaming velocities, and redshift. So, Mihir, are you there? Hello, Mihir?
Sorry, yes. Can you hear me?
Yeah, now we can hear you. Maybe make it slightly louder.
Okay. Thank you for this opportunity. I'm Mihir Kulkarni. I'm a graduate student at Columbia University, and I'm going to talk about work that I've done with my advisor, Greg Bryan, and Eli Visbal on critical halo mass for population 3 stars. So critical halo mass can be defined as minimum halo mass that is required to host sufficient cold and dense gas that can lead to formation of stars. And in lambda CDM, this is expected to be somewhere between 10 to the 5 to 10 to the 7 solar mass halos. And in particular, depending on the environment or various feedback processes, this critical mass can increase. And in that scenario, population 3 stars form in massive halos and their formation is delayed. Having an accurate estimation of this critical mass and how it depends on the environment and feedback processes is very important for semi-analytic models, as mentioned by Eli Visbal or Tilman, Hartwig, which use dark matter only simulations. It's particularly interesting time to study them, as Anna Schauer also had a recent paper looking at the same problem using ARIPO simulations, and our results are in broad qualitative agreement, but we still see some differences in detail which need further investigation. So in the mini halos, the virial temperature is few thousand Kelvin, and in absence of metals, molecular hydrogen is necessary for cooling. And Lyman-Werner photons can dissociate the molecular hydrogen. And as you form more and more first stars, they build up a background of Lyman-Werner radiation, which can destroy molecular hydrogen and suppress star formation. However, massive halos can self-shield themselves from Lyman-Werner radiation. Therefore, population 3 stars form only in massive halos, therefore increasing critical mass and delaying their formation, which is one effect. Other effect which can also increase critical mass is streaming velocity between baryons and dark matter, which was introduced after recombination. Prior to recombination, baryons were coupled with radiation, whereas dark matter was not, and its fluctuations grew on its own. This resulted in a net streaming velocity between baryons and dark matter, which is a very large-scale phenomenon, but it's coherent over 3 to 5 moving parsec. It follows a Maxwell-Boltzmann distribution of root mean square velocity of 30 kilometers per second at recombination. It decreases with time as 1 plus z, so it is particularly important for high redshift phenomena such as population 3-star formation. And in particular, in regions of high streaming velocity, halos are gas poor and have a lower maximum density, as baryons have a net velocity with respect to dark matter. And therefore, halos again need to be more massive with deeper potential wells to have sufficient gas densities, which results in increased critical mass and delaying population 3-star formation. So we can understand this by looking at a slice of gas density overplotted with gas velocity in the initial conditions at redshift 200. The slice on the left shows case without any streaming velocity, where the velocity follows the structures that we see, whereas the plot on the right has an added streaming velocity in the x direction. And what we can see is on top of the added streaming velocity in the x direction, we also see that some of the small scale structure is also erased, which is included through perturbation theory on the effect of streaming velocity from recombination to the redshift of initial conditions. So to understand the effects of Lyman-Werner background, streaming velocity between baryons and dark matter, as well as redshift, as had been predicted in many analytic models, we performed a cosmological simulation suite using ENSO. We included primordial chemistry, and in particular, including molecular hydrogen, which is necessary for cooling. And we included initial conditions using KICAS initial conditions generator, which treats streaming velocity between baryons and dark matter accurately in the initial conditions. And we use very high spatial resolution as well as mass resolution in our simulations. For specific runs with high streaming velocity and Lyman-Werner background, we use larger boxes with slightly lower resolution. And in our simulation, we identify a halo as having cold and dense gas if there's at least one cell in it which has temperature less than half the virial temperature and density more than 100 cc. And for all those halos, the cooling time of the gas is shorter than the Hubble time at that redshift, which has been used as a criteria for identifying critical mass in previous analytic models. So to understand the effect of Lyman-Werner background, we used 4 different Lyman-Werner backgrounds. We also included some very high Lyman-Werner background cases, and we included 3 different streaming velocity cases. Also, in order to test the previously made assumption whether the increases in critical mass because of streaming velocity and Lyman-Werner background are independent of each other, we also included few runs where both these effects are present. So this plot shows halo mass on the x-axis, and y-axis denotes corresponds to 0 if that particular halo has no cold dense gas, or corresponds to 1 if that halo has cold dense gas at a given redshift. And what we can see is the transition from warm halos to cold dense halos does not happen as a step function in halo mass, and there's a significant scatter in the mass range where the transition happens. Therefore, we identify critical mass corresponding to a mass where 50% of the halos at that mass have cold and dense gas. And we also return an estimate of the scatter that we see, which corresponds to mass range where 25 to 75% of the halos have cold dense gas, and we return that in our paper as well. So if we look at some of our results, so this plot shows critical mass that we see as function of redshift on the x-axis for various different Lyman-Werner backgrounds for case without any streaming velocity. And first thing we can notice is for the case without any Lyman-Werner background radiation, we see a redshift evolution of critical mass, which is consistent with a fixed virial temperature that would correspond to 1 plus z to the minus 1.5, as had been predicted in many analytic models. We also find that increasing Lyman-Werner radiation as we go from 0 to 13 units of J21 increases the critical mass up to 2 orders of magnitude for very strong Lyman-Werner background radiation. What we also find is the redshift dependence of critical mass becomes more and more steep as we increase Lyman-Werner background, going to as high as 1 plus z to the minus 5.7 for very strong Lyman-Werner background radiation. And we also find that the self-shielding of molecular hydrogen is very important. And we find for a Lyman-Werner background of J21, we find that our critical mass is much smaller than previous works like Mahachek et al., which did not include self-shielding of molecular hydrogen and is very important. This plot again similarly shows effect of critical mass as function of redshift for 3 different streaming velocities without any presence of Lyman-Werner radiation. And again, as expected, we see that in regions of high streaming velocity, critical mass is increased. And we also see that the redshift dependence, however, changes in the opposite direction. In the regions of high streaming velocity, the Z dependence becomes less steeper. And we can see that for a case with 2 sigma streaming velocity, the redshift, it becomes nearly redshift independent. And this can be understood using the fact that streaming velocity decreases with time as 1 plus Z. So we expect the effect of streaming velocity to be more prominent at high redshift, which can explain this particular trend that we see. Now, when we have both Lyman-Werner radiation and streaming velocities, we can ask if the effects of both these processes are independent of each other. And here on the y-axis, we show increase in critical mass when we include Lyman-Werner radiation. So the solid line, for example, here shows increase in critical mass when we include Lyman-Werner radiation of 10 J21, and how much by what ratio the critical mass increases without any presence of streaming velocity. And the dashed line shows similar increase from same Lyman-Werner radiation, but in a region of high streaming velocity. If the effects from both the processes were independent of each other, we would expect that the solid lines and dashed lines would overlap with each other. But on the other hand, what we find is if we are in the region of high streaming velocity and Lyman-Werner radiation, the combined effect is less effective or less strong than what we would expect from an independent assumption. Now, to understand some of the trends of critical mass, particularly with redshift, it may be helpful to look at the quantities at the densest cell in our halos. So in here, I show the quantities at the center of the halos. On the column on the left shows case without any streaming or Lyman-Werner background radiation. Okay. The middle column shows case with only Lyman-Werner radiation, and the column on the right shows only with streaming velocity. And the red dots denote halos that do not have cold dense gas, whereas the blue dots denote halos that have cold dense gas. And we can use the trends for warm halos and how they change as function of virial mass as well as redshift to propose a simple analytic models to explain the observed redshift dependencies that we see. In particular, in presence of Lyman-Werner radiation, we see that the molecular hydrogen is suppressed. And we see that for even halos which have mass slightly less than critical mass, the molecular hydrogen fraction has already started to increase. To understand that, we can also look at the effect of self-shielding that I had mentioned. So in this plot, we show self-shielding factor as function of virial mass of the halos. And the self-shielding factor of 1 corresponds to no self-shielding. And we can see that we find significant self-shielding, and we also find that molecular hydrogen appears to be in equilibrium. And the self-shielding is important to explain why we see steeper redshift dependence for MCRIT in presence of Lyman-Werner background radiation. To summarize, we find that critical mass depends is consistent with a fixed virial temperature in absence of Lyman-Werner radiation and streaming velocity. And Lyman-Werner background increases critical mass as well as increases redshift dependence. We also find that self-shielding of gas from Lyman-Werner radiation is important and needs to be included. And we also find that effects from Lyman-Werner radiation and streaming velocity are not entirely independent. And finally, we provide a fitting function for this updated critical mass as function of Lyman-Werner radiation, streaming velocity, and redshift, which can be used by semi-analytic models as explained by, for example, Eli or Tilman. Thank you.
Thank you, Mihir. Again, let me just ask one of the questions from Slack, and then you're encouraged to check out many other questions there. So Anna Schauer asked, why do you think that your halo masses are lower than in her paper this year? Do you have
right. Yes. Yes. So we see similar increase in critical mass, for example, from streaming velocity. But even if we include case without any streaming velocity and Lyman-Werner radiation, we see critical mass of the order of few times 10 to the 5, which is nearly an order of magnitude smaller. I can think of various possible explanation. One could be exactly what definition of virial mass we are using. For example, Rockstar returns different masses and we use M200C, but that cannot explain the complete differences. So I think to understand that in detail, it would be helpful to make one-to-one comparison looking at the central quantities that we see.
Can you say how large are the differences? Are they a factor of 2 or 5?
Right. So in absence of any Lyman-Werner background and streaming velocity, we see close to 2 to 3 times 10 to the 5. Whereas I think in Anna Schauer's paper, they see close to 10 to the 6.
Okay.
Right. Yeah. So roughly factor of 5.
Yeah. Thanks, Mihir. Let's move to the next talk, which is by Kirk Barrow. And Kirk will tell us about unraveling time-dependent trends in star formation using cosmological simulations.
Hi. I think his is still up.
Yeah, Mihir, can you stop sharing? Yeah.
All right, just an audio check. Can you hear me?
Yeah, that's perfect. Thanks.
Great. So hi, I'm Kirk I'm a postdoc at Stanford University. And this title seems like what everybody's doing, but I'm coming at it from a little bit of a different angle. And to sort of introduce my work a little bit, I wanted to put up this really simple map. So you can think of the beginning of the universe as the left side and the present day as the right side. And, as Eli said, cosmological simulations, hydrodynamic simulations are computationally expensive. And in order to sort of move to the present day with them, you have to either make sacrifices in terms of their size or complexity, or you just can't do it. And then, of course, on the telescope side, we have a fairly clear picture of what's right next to us. And as we go deeper into deeper fields, it becomes a lot hazier. And of course, we don't have a direct sort of infrared or optical view of reionization, and we're waiting for that with telescopes like JWST. So my research is focused primarily on a region of overlap. And that region of overlap is, it's not focused on a particular redshift. It depends on the way that you're overlapping observations and cosmological simulations. But no matter, what you think of as the overlap region, you have to speak a common language between the two sort of different fields in order to iteratively improve our understanding of the universe. So the common language, I think, is through light. And that means that I need to make from cosmological simulations something that looks like what the observers see, which is luminosities, images, spectra, and things like nebula emission lines. So nebula emission lines are important for a lot of reasons. So, as we know, nebula emission lines are really sensitive to really small changes in the hydrodynamic environment where they're created. And they, therefore, because there's so many of them, they sort of serve as a fingerprint for the environment of the galaxy. And you can sort of understand a lot about what happened to that galaxy from the nebula emission lines. On the modeling side, it's actually somewhat of a difficult problem to reproduce nebula emission lines because they're sort of produced all throughout, in inhomogeneous H2 region. So if we sort of look at this toy model of an AMR simulation, nebula emission lines are not just coming from the cells that contain star particles, they're actually coming from all the cells in some form or fashion. And the H2 regions that are produced when these star particles are not spherical, they're not, the gas is not homogeneous, and you have to think about all the different combinations that you could have and the full radiative environment in order to reproduce a nebula emission line. But it's worth it because if you can reproduce nebula emission lines, then you can talk directly to observers about the detailed microphysics, the kind of things that we're talking about during this conference, the star formation physics that occur inside of galaxies. So hopefully I've convinced you that nebula emission lines are important, because I haven't heard them talked about too much so far. But I think a lot of people agree that time domain studies are important. Almost everybody so far has done something in the time domain and talked about the redshift dependence. But working on synthetic observations, I didn't start in the time domain. I actually started with the Renaissance simulations that Eli brought up. And I took one single snapshot and looked at all the galaxies within that snapshot, made synthetic images and spectra and nebula emission lines. And it was a good statistical sample. But from a single snapshot, of course, you can't figure out where, directly you can't figure out where all of these relationships came from. And you really need to think about a dynamic, the full dynamic environment to really understand where all of these observables are actually coming from. So while we wait for that region of overlap between observation simulations to move into reionization with JDVST and maybe a moon colony with a big telescope, one of the things I've been doing is I've been looking at how do we move a little bit closer to the present day and make comparisons with observations we've already seen. But I want to motivate time domain studies, especially when it comes to not only galaxy formation, but with observations. So why do we need time domain studies at all? And why don't we just use a semi-analytic model to make up for that with, instead of using those really computationally expensive hydrodynamic simulations? And the reason is because early universe galaxies, or one of the reasons, early universe galaxies have birthday star formation histories. They're irregular. You can't really always assume spherical symmetry. They have high merger rates, and mergers are really messy processes. So this sort of challenges a lot of the semi-analytic notions. And when it comes to reionization, this is where we really need to get these things right. So these images I'm showing in the background of these movies are, Monte Carlo ray tracing optical images of galaxies. So here's two galaxies merging. And these events that happen, these really large star formation events that happen, these small halos, they're really disruptive. And if you don't get the feedback right, if you're not modeling all of the feedback, you might actually miss the boundary between a galaxy that continues to form stars and goes about its business, or a relic galaxy that's completely disrupted. Like, you need to really understand the difference, because if you're trying to make predictions for observations, those are two opposite scenarios. You really need to understand that difference. And then the last, pitch I'll make for doing time domain studies with synthetic observations is that if you look at a single snapshot like I did, in order to produce that snapshot, of course, you've calculated all the intermediate time. And it sort of turns out that the parameter space of synthetic observations for a single galaxy is quite large over its history. And so to only look at one time step is to throw out all of that information you've already calculated. That is actually quite as interesting as any individual time step. Okay, so let's talk a little bit about the first stars and this critical mass question that keeps coming up. Now, before Mihir's talk, I would have said, okay, I have a wonderful simulation with really high resolution, and that minimum mass shown in the top left as this vertical line seems to be consistent with Anna. I'll have to look at that again in case things are changing a little bit. But one of the interesting things, I think, to some of the other presenters and in the audience is actually this internal enrichment, external enrichment question. And what I'm seeing is that, as people talked about, that a dynamic fully resolved, hydrodynamically calculated external enrichment is actually causing a, it's actually suppressing population 3-star formation after some point. It's changing the critical mass, and these processes really need to be untangled before you make sort of broad sweeping statements sometimes about the critical mass. And this is something I'm really interested in looking into in the future. But that's not the whole of my wheelhouse. My whole of my wheelhouse is mostly in synthetic observations. So these hundreds of galaxies that I'm simulating are going to be turned into synthetic observations. And you know, you kind of caught me while I was working on that, but I want to show an example of where that comes in. So this is an example of synthetic observations that you can make from a single galaxy. So you have the spectra, you have the emission lines, you have escape fractions, you have the galaxy. But how do we actually use this to answer questions with observations? So here's a bunch of observations. This is the emission line ratio between O3 and O2 versus the escape fraction ionizing radiation. And the question was, why do we see the top left of that chart, why is it empty? Now there's some lines you see in there. That was based on sort of preliminary observations, and that's sort of been debunked a little bit by the present observations, but there's still this missing part on the left side. And how I sort of looked at this is that first, I had my toy model to see what happens with a single cluster, and it turns out that emission lines are actually quite sensitive to different phases in this evolution of stars. And then I have my full model, which solves the full radiative environment and creates emission lines throughout the galaxy in sort of a generalized way. And you can actually see as the yellow line, the ratio between the lines. And I found that the escape fraction of ionizing radiation and O32 were offset because of the different timescales of the processes, where O32 was really, O23 was really responsive to recent star formation, and then the escape fraction had a longer delay time. And it sort of turns out that because I'm looking at all of the time, all of the history of this galaxy, so there's actually thousands of outputs that have analyzed and created synthetic observations for. And then the orientation of the galaxy is important for escape fractions, particularly because the escape fractions are highly anisotropic process that really depends on the morphology of the galaxy and where the neutral gas is. It turns out that you can create millions of possible synthetic observations from a single galaxy and start to reproduce the observational landscape shown here. So this is sort of my most recent work, but what I'm really looking forward to is turning that reionization simulation into hundreds of copies of that and creating a predictive landscape for our next generation of GMT and our large telescopes, as well as JWST. So that's what you can look forward to from me. And to summarize really quickly, you should care about number emission lines because they're going to help us solve some of these questions. Time-dependent studies are good. And it turns out that O32 is not linked to escape fractions in a causal way. It actually has to do with a timing issue. So I'll wrap up there. Thank you, and I'll take some questions.
Thanks, Kirk. This is great additional information on the early star formation. So I actually I don't yet see any questions on Slack, but I did have several. Let me just ask one because we're also slightly late. Is just observationally, can you give an idea of, are these lines all going to, how many or which lines are going to be measured at high signal to noise by JWST and GMT? And do we have do they even resolve the kinematics or width of these lines so that we can study them in some detail?
I mean, that question depends on redshift. I'm actually
let's say redshift 10. I mean, can you go into the to the halos at the critical mass and see their nebular lines? And to
I don't expect you to be able to go to the critical mass, but I will say that when I speak about emission lines, you know, after sort of basing my initial postdoc proposals on JWST, I've sort of I was taken to overlapping with current observations, so things at redshift 3, 4, 5, and 6. And so if you're waiting for the most forthcoming things that you're going to see from me are going to be focused in that era. So we'll see what GMT provides, and I'm really looking forward to JWST as well. But I don't, though, predict that the critical, so maybe in the future, maybe on side, we can talk about that. I think there's a way that you can constrain that from what happens at redshift 5 and 6, but I think that's a different question.
Okay, so maybe, so now you do have a lot of questions that popped up, including people want your movies shared. So do go to Slack. Let me just ask one of the questions, which is, if you smooth this from Yu Chiang Chin, if you smooth the escape fraction over a longer period of time and introduce time delay, would it align better with the 032 indicator?
No. So the initial, and I didn't have really time to go into the depth of that. So the initial thought, I guess not really initial, from like early 2020, was that the reason that they're related in any way is maybe because you're seeing the 032 through the same ionized channels that you're seeing escape fraction. And it sort of turns out that that can't be, because 032 is an optically thin line. It isn't absorbed by the medium, so it shouldn't really be related to escape fraction. If escape fraction is something that is related to the orientation of your line of sight. So, but to answer your question about smoothing it over, no, there's sort of a systematic delay between the formation of a star cluster and the ionizing radiation actually getting outside of the galaxy. So, and there's almost no delay. There's only a few million years delay for the 032. So there's just sort of a systematic difference between the two. And I invite you to read my paper to read a little bit more about that.
Thank you. Thanks, Kirk, again, for a very nice talk. And let's move on to the next one. So next talk is by Louis Welch on the stochastic enrichment of near pristine systems, POP2 stars versus the most metal-poor damp Lyman alpha absorbers. So, Louis, are you there?
Hello, yes, sorry. I just need to share my screen again.
Yeah, please do. Thank you.
Great. So hi, everyone. Yes, my name is Louise, and I'm a PhD student at Durham University. And so today I'll talk about the chemical enrichment of some near pristine systems, focusing on trying to search for the chemical signature of population 3 stars in a sample of metal-poor Milky Way halo stars. And just for some motivation, or so how we do this, we have to kind of understand the expected chemistry of these massive metal-free stars. So we can look to simulations of the evolution and explosion of massive metal-free stars to get an idea of the chemical yields that we'd expect for a range of different stellar properties. And so I've been using the simulations from Hager and Woosley, performed in 2010, and they calculate the yields of population 3 supernovae as a function of the progenitor star mass, the explosion energy of the supernovae, and also the degree of mixing between the different stellar layers. So in this figure, I'm just showing the magnesium to calcium and nickel to iron abundance that you would expect for a range of different stellar properties. So the panels in blue correspond to when we have a nominal mixing between the different stellar layers. And this corresponds to mixing width that's around 10% of the helium core size. And then the yields that I'm showing in orange correspond to the case when the mixing between the stellar layers is more minimal, so it's around 1% of the helium core size. And the different colored lines here are corresponding to different energy explosions, where as you go to lighter lines, you get progressively higher energy explosions. So the key takeaway from this figure is that if you have a system that has been enriched by one population 3 supernovae, then if we know the detailed chemistry of that system, we can work back to find the properties of the population 3 star that's enriched it. But as we've heard from talks by Chiaki earlier, it's possible that these surviving relic objects may have been enriched by multiple progenitors. So something that's useful to do is construct this stochastic chemical enrichment model, where we're trying to gauge the number of massive population 3 stars that have chemically contributed to a given system. And so here I'm showing the model that I've been working with, where the stars are forming obeying an underlying mass distribution that's governed by a power law, and the slope is given by this parameter alpha, and the stars are forming between a given minimum and maximum mass. And in addition to the mass distribution of these enriching stars, we're also trying to gauge the energy of the supernova explosion and also the mixing between the different stellar layers. And the key benefit to a model like this is that because we expect the metal-free stars to form individually or in small multiples, your underlying IMF is going to be stochastically sampled. And that means that the observed distribution of abundances, like magnesium to calcium, that you would expect to see across these relic objects will change depending on the average number of stars chemically contributing to each system. So you can see in this figure here that as your objects are being enriched by more and more stars, this distribution of magnesium to calcium is getting more and more centrally concentrated. So using this model, I've tried to look at the chemical enrichment of a sample of metal poor halo stars, whose iron to hydrogen abundances are all less than -2.5. So they're at least 300 times more iron poor than the sun. And the stars that I've been using come from 4 historic surveys. So there are 2 samples from the first stars series and also 2 more recent surveys from David Young and Ian Roderer. And in my analysis, I chose to look at the relative abundances of magnesium to calcium and nickel to iron of these stars. So here I'm showing you the abundance distribution of these elements for the 4 different samples. And you can see that they're broadly consistent with one another, but there is a small offset in the magnesium to calcium abundances between the data from the 2014 sample and that of the other samples. And it turns out that while this offset is very small, it's only around 0.1 dex, it does have an impact on the enrichment model parameters that we estimate. So it's actually been very useful for testing the sensitivity of our model to the input data. But for now, I just wanted to highlight the results that we found when looking at the 3 samples compiled before 2014. So here I'm showing the estimated enrichment model parameters for these 3 samples. And we found in general that these stars were preferentially enriched by minimally mixed hypernovae, but the key parameter that I wanted to talk about today is the number of enriching stars that we find. So if we just zoom in here to the region that occupies the 1 sigma confidence region of our parameter estimate, you can see that we found around 5 massive population 3 stars seem to have chemically contributed to the sample of metal poor halo stars used in our analysis. And this is quite interesting, I think, given Tilman's talk earlier in his plot with his work with Mihir Kulkarni. It seems like we're finding similar numbers of enriching stars for these stellar relics. So that should be quite cool. But one thing that you may be asking is how well can this model actually replicate the data? So here I'm showing the magnesium to calcium abundance and the nickel to iron abundance that you would expect given our inferred enrichment model. And overplotted on that density contour is our stellar data coming from the 3 samples prior to 2014. And you can see from this figure that the model and the data are broadly consistent with one another, but there is still this small offset between magnesium to calcium. And so improvements can still be made, and some recent work by Rana Ezzedine suggests that non-LTE corrections to magnesium to calcium may bring our model and data into better agreement with one another. And another thing to be aware of is the idea that if we perform these simulations of stellar evolution in 3 dimensions, it might also influence the fit between our model and the data. And another thing that I thought was quite interesting to do with this work was to look at the chemical enrichment of low mass structures in the early universe. So prior to this, I've really been looking at the chemistry of near pristine gas, thank you, in the early universe, so these metal poor DLAs. And in some previous analysis, I estimated the number of enriching stars for these systems. And so by comparing the number of enriching stars across the metal poor DLAs and this analysis of metal poor stars, under the assumption that the number of stars enriching a typical metal poor halo star is comparable to the population 3 multiplicity, then we can start to infer the number of population 3 mini halos that have chemically contributed to the low mass structures at a redshift of 3. So here I'm just showing the posterior distribution of this parameter and halos. And you can see by the gray dashed line that our 2 sigma upper confidence limit suggests that less than 13 population 3 mini halos may have chemically contributed to the metal poor DLAs I analyzed last year. And finally, I wanted to briefly highlight some more recent work we've been doing using the carbon isotope ratio that I think fits in quite nicely with the next talk coming up. So here I'm showing the carbon 12 to carbon 13 ratio as a function of progenitor mass that you would expect for a range of different stellar populations. And you can see that the only way to produce low amounts of carbon 12 to carbon 13 is through the low mass population 3 stars, shown in purple, or the intermediate mass population 2 stars, shown in gray. So the idea here is that if we can detect this carbon isotope ratio in a near pristine system, we may be able to detect the presence or absence of low mass population 3 stars. And so recently, using Espresso, we've placed the first bound on this carbon isotope ratio in a near pristine DLA. And we could rule out the presence of large amounts of carbon-13, but we couldn't empirically rule out enrichment from low mass population 3 stars with the current data. And that brings me on to my conclusions, which are that early stellar populations can be investigated using the surviving chemical signature left behind by their core collapsed supernovae. And this enrichment model takes into account the stochastic nature of the population 3 IMF. The most metal poor stars appear to have been minimally enriched by massive population 3 stars. And the combined analysis of these stars and the most metal poor DLAs may offer a way to look at the number of population 3 mini halos that contribute to a low mass structure at a redshift of 3. And finally, we've recovered the first bound on this carbon isotope ratio in a near pristine system. And with future data, we are hopeful that we may be able to rule out enrichment from low mass population 3 stars. So, thank you.
Oh, thank you, Louise, for a wonderful talk. Very interesting. We do have several questions. Let me read out one from someone who hasn't yet asked the question. So Asas Kuladotir says, very nice talk. Do you see any correlation between Fe over age and the number of enriching stars?
So, sorry, something age and the enriching stars?
Do you see any correlation between the iron to hydrogen ratio and the number of enriching stars? In your
that's interesting.
Example of metal poor halo stars.
Yes, so I think something that we should do definitely is look at even lower metallicity stars. So with a cutoff of iron to hydrogen of -3 and below, and see if the number of enriching stars does go down. I don't have any solid evidence to say on that yet, but it is something that we want to look into. And I am hopeful that there would be a correlation, but of course, yeah, I don't know.
Okay, so another question is, have you thought about doing this analysis with dwarf metal poor stars in dwarf spheroidals?
Yes, we would love to do that, but the problem, I think, if I remember rightly, is that there aren't that many stars in these systems that we can use, and yeah, I think that was the main impediment. So Segway 1 was one of the places that we tried to conduct this, but I'm not sure on the numbers. But yeah, I think we were limited by low number statistics, especially looking at an individual dwarf. Yeah.
Okay, here's one more quick one. Is what is the mass of the halos that pollute the DLAs?
The mass of the the halos that pollute the DLAs. That's a good question. I don't know. But the general idea is that when we're modeling the enrichment of the DLAs, we assume that the stars have come from multiple population 3 mini halos. So presumably more than 1 10⁶ mini halo. And then however many, these DLAs are likely hosted in some of the lowest mass structures at that redshift interval. So yeah.
Okay, last quick one is also Alex G asks, awesome Luis, I'm wondering if you redid this using POP2 instead of POP3 yields.
Yeah,
it does differ.
That's a good question. I don't know. There are all so many good questions. I don't know the answer to that.
More, by the way. So yeah, you're encouraged to go to Slack as well. There's more questions there.
Okay. Yeah. My brief answer is I don't know. Certainly, for other elements like carbon and oxygen, you have very similar yields for population 3 and population 2 stars. So it would be unlikely to make a difference in that case. But for these elements, I haven't checked, so I don't know if that's the same.
All right, thanks very much again. And we're ready for hearing last but not least from Martina Rossi, who will tell us about constraining the low mass end of the first stars.
Okay, can you hear me?
Yes.
So first of all, thank you for giving me the opportunity to present our results. And in this talk, we will talk about how to put observational driven constraint on the low mass end of the first stars. So as you know, one of the most fundamental unknown regarding the first stars is their mass distribution. Especially at the moment, we don't know what is the shape of the AMF. We don't know if it could be top heavy or flat. In addition, we don't know what is the maximum mass for POP3 stars, if it could be greater than 100 solar masses up to 1000. And finally, what about the minimum mass of POP3 stars? Where POP3 stars with low mass were able to form, we don't know. So, but why low mass end of the first stars is so important? Well, we know that the lifetime of a stars is closely linked to their mass. And especially POP3 stars with mass below 0.8, they have a lifetime that is greater than the age of the universe. Therefore, if POP3 stars with this mass were able to form, they could survive as a living relics of POP3 stars. This is why constraining the low mass end of the first stars is so fundamental, because it determines if we will be able to see them or not. So in our local group, we look for zero metallicity stars among the most ancient and the least chemically enriched system, like the halo and the bulge of the Milky Way, in dwarf galaxies, and especially in ultra-faint dwarf galaxies, Milky Way satellites. In fact, these systems are the least luminous and the least iron abundance ever known. Furthermore, if you look at the color Maillard diagrams, they show that they had a very short star formation history, and they have a very ancient stellar population with age greater than 10 gigayears. So are the best system to look for zero metallicity stars. In our work, we focus on Bootes-1, that is one of the best studied ultra-faint dwarf galaxies, both observationally and theoretically. So we choose as a target. The aim of our work was to constraining the low mass end of the POP3 stars using the non-detection of zero metallicity stars in ultra-faint dwarf galaxies. To do this, we developed a semi-analytical model that describes the evolution of a Bootes-like ultra-faint dwarf galaxies from the epoch of this formation up to zeta 0. The model includes all the most important physical processes, and we calibrate the model using chi-square statistic. In particular, we calibrate the model in order to reproduce the observed properties of Bootes-1. Here we show the average iron abundance as a function of the total luminosities, and the points represent the data available for ultra-faint dwarf galaxies Milky Way satellites. As you can see, the color delineates the chi-square confidence level contour, and our fiducial model is represented by the yellow stars. As you can see, in the 99% of confidence level contour, we have Bootes-1, but also other two ultra-faint dwarf galaxies that are Hercules and Leo 4. This means that our model is able also to reproduce the properties of these ultra-faint dwarf galaxies. So for our fiducial model, we derive the metallicity distribution function, that is the number of surviving stars up now, as a function of their iron abundance. In the plot, we show the data in red, and in blue, our simulation. As we can see, there is a very good agreement between observation and simulation. Of course, since any POP3 stars has been observed so far, we set the minimum mass of POP3 stars equal to 0.9 solar masses to calibrate the model. However, these results are obtained assuming too fully populated the mass distribution. So we ask ourselves, is it a good approximation for poorly star-forming ultra-faint dwarf galaxies? The answer is not. In fact, as we can see on the left, we show the evolution of the star formation rate. On the right, we see the comparison between the theoretical IMF in red and the effective IMF resulting from the Monte Carlo procedure in light blue. As you can see, in the first evolutionary phase of the galaxies, the IMF is poorly populated. And even at the peak of the star formation rate, the effective IMF does not converge to the theoretical one, especially for mass greater than 10 solar masses. So we explore what is the impact of the random sampling of the IMF on the expected number of zero metallicity stars in Bootes-1. And what we found is that the fraction of zero metallicity stars increases a lot. So then we explore what is the impact of different IMF, POP3 IMF on the expected number of zero metallicity stars. And in particular, we choose 4 different IMF with three different characteristic mass and the decays of the flat IMF. We also vary the maximum and the minimum mass of the POP3 IMF. And the results are shown in this plot, as we can see in this plot, we show the fraction of POP3 stars with respect to the total as a function of the minimum mass for different IMF. And what we can see is that the higher is the characteristic mass of the IMF, the lower is the fraction of zero metallicity stars. In addition, for characteristic mass 0.35, there is a dependence of the on the minimum mass of the POP3 stars, while for all the other IMF, the fraction is independent from the minimum mass. If we consider a higher maximum mass for POP3 stars, as you can see, our results does not change if we assume a maximum mass equal to 1000. So, using a statistical approach, the one of Hartwig, we can derive what is the sample size of the stars that we should observe in order to constrain the minimum mass of the POP3 stars. So here we show the sample size as a function of the minimum mass for 3 different confidence level, and the red shaded area represent the stars that have already observed, we have already observed in Bootes 1. And as we can see, only using 41 stars observed in Bootes, we can already exclude that the POP3 stars have minimum mass below 0.8 solar masses. If you remember, our model is able to reproduce also the properties of Hercules and Leo. And if we consider also these, the total number of stars observed, that the cumulative number, and we derive the same plot for characteristic mass 1, we can conclude that the characteristic mass of POP3 stars should be greater than 1, or the minimum mass greater than 0.8 solar masses at 68% of confidence level. However, it's clear that more observations are needed to put strong constraint on the IMF, on the minimum mass of POP3 stars. So, but what does it mean observe a larger sample size in terms of observation? So to answer this question, we derive the theoretical CMD for Bootes 1 in order to translate the sample size in terms of magnitude. As we can see, the current limit is set at magnitude equal 19. However, ELT will go deeper in the observation. So we can ask ourselves how deep the observation should be in order to put constraint on the characteristic mass of the IMF. So as you can see at the moment, we can say something about only characteristic mass around 1 solar masses. However, ELT, with the ELT and with deeper observation, we will able to get a strong constraint on the characteristic mass of the POP3 stars. So in conclusion, we can affirm that ultra-faint dwarf galaxies are the best system to put constraint on the minimum mass of POP3 stars. And only using 100 of stars, we can start it to see that it is very unlikely that POP3 stars have low mass. And an important thing is that the random sampling of the IMF is required if you want to describe correctly the ultra-faint dwarf galaxy systems. So our result, so stay tuned. Our result will be published soon. Thank you. I can hear you.
Sorry, thank you very much for a very interesting talk. Let me ask a couple of questions. So first one is the issue which Tilman also mentioned, surface accretion of metals after the low mass stars form. Could it be that there were low mass POP3 stars, but they no longer appear metal free because they accreted metals?
Yes, but we don't take in consideration this study. We assume that POP3 stars form when the IMS have a metallicity below the critical one. So we don't take in consideration any kind of pollution for POP3 stars.
And then another question that came up by a couple of people is ejection. So low mass stars early on might be ejected from their parent mini halos where they were formed. Could it be that they formed that you assume a closed box system? I assume you sampled the IMF.
Yes, because
could we have lost them due to ejections?
Yes, we described the evolution in isolation for Bootes 1. And we don't have spatial information about of the galaxy. This is a semi-analytical model, and when there is a sufficient amount of gas, we assume to form stars. So we assume that all low mass POP3 stars remains inside the halo.
Okay. So I think I'm tempted to, I think we started losing some people from the Zoom. So I think people might have commitments at 1. So I think we should wrap up. We're only 2 minutes over. I want to thank all the speakers in both sessions, actually. I also want to thank Anna for leading the organization of this conference. We had more than 100 people. I think 114 was the max. So clearly it was something worthwhile. Anna, did you want to say something before we break up?
Yes, Sultan, thank you so much. And thank you everyone for talking. I love the talks. I wish we could continue for hours, but I think it's very late for some people. So let me quickly just show you a representation of those more than 100 people, and I think 30 people in addition on YouTube. So we have a conference picture. If you don't find yourself in there, please just message me and I'm happy to include you. I can fiddle around with that. And then finally, after the conference is before the conference. So there will be another SAZERAC-Sip about quasars during reionization. There's still a little bit time for abstract submission. The deadline is November 5th, and the conference will take place early in December. So I encourage everyone who works on quasars or supermassive black holes to take a look at that. And with that, thank you so much, everyone, for attending. Thank you so much to my SOC, to the 2 Steves, to Will. It was a great 4 hours. I enjoyed it, and I hope I see you soon, maybe even in person. Bye.
Can I also just say,
Absolutely.
I really enjoyed the talks a lot and would love to have the slides. So the speakers would be great to post them on the talks and PDFs on the website.
Yeah, I've already seen 2 people posting them on Slack in the threads, and I'll coordinate with the Steves if it's possible to even put them on the web page. And then speakers, please either upload them on Slack or email me if you would like them to be shared.
Yeah, all the talks will be recorded anyway and available on YouTube, so you should be able to access the slides that way at the very least, unless anybody doesn't want to do it. Thanks, Anna.
Thank you, Anna.
Good to see you.
Thank you, everyone. Have a great
Thanks,
weekend.
Anna.
Thank you.
Thank you.
All right, thank you. Bye.
Thanks a lot. Bye.
Anna, well done, that one really well. It's really
Thanks.
dark in here now.
Yeah, I thought it was great. I learned a lot.
Yeah, me too. And I'm excited to go back to all those threads and read all those questions on Slack.
Yeah, actually, there's a lot of them.
Yeah.
I think it's impossible. It would have been nice to have discussion time, but I think it's just impossible.
Yeah.
Time zone constraints.
Yeah, I think so too. So
to allocate discussion time and have a fair number of talks. So
yeah.
I'm gonna read the Slack.
Me too. It would be great to now go for a coffee with the speakers that gave an interesting talk. That's like where you still have open questions too. But latest in New York.
And look, we can see the people who all fell asleep. There's only 70 of them.
All right, and thanks, Steven, also for the help. Yeah.
Yes, thank you. That made things so much easier.
Well, thanks again for organizing it. It went really well. I'll let you know when we get the videos processed. I think Will's going to try and do it.
So I actually, yeah, that would be. And I missed actually. Did you ask? Maybe I missed that. Is the PDFs? Did you ask the speakers to put the PDFs on Slack?
I didn't ask them to, but two did anyway.
But they did it. Okay. Yeah,
Yes,
yes.
you should at least have the video recording so you can actually see the slides in the recording itself. So we'll at least have that. But yeah, feel free to ask people, and we can figure out a way of putting the PDFs on the website. If that's because it's a relatively small number, it should be easy just to do it manually. So I can do that quite easily.
Okay, so if there's the possibility, then I'll just email all of the speakers and tell them if they want them completely public, they should email me or maybe you directly the slides. And if they want them semi-private, they can put them on Slack.
Yeah. Cool. Great.
Awesome.
Thanks again.
All right. Bye.